Hello stargazers and dreamers. I'm Atlas Reed, and this is the Nocturnal Astronomer, your gateway to the cosmos through the gentle embrace of sleep. Tonight, we embark on a very special series of extraordinary journeys that will carry you from the quantum dance of atoms in your very body to the vast, mysterious structures that shape our universe. These aren't just bedtime stories, they're invitations to drift peacefully through some of the most profound and beautiful phenomena that science has revealed. You'll discover how the atoms within you once blazed inside ancient stars, feel the subtle ripples of gravitational waves washing over Earth from cosmic collisions billions of years ago, and travel through the cosmic web, that magnificent scaffolding of dark matter and galaxies that gives structure to everything we see. We'll explore how time itself bends and stretches in ways that would make your daily experience seem like just one small note in an infinite symphony. Listen as neutron stars sing their magnetic lullabies across the void, discover how ancient light carries whispered stories from the universe's childhood, and follow our own Milky Way as it drifts slowly toward the Great Attractor, a mysterious gravitational pull that beckons from 250 million light-years away. Each story is crafted to let your mind journey freely through these cosmic wonders while your body finds the deep rest it needs. Whether you're fascinated by the science or simply seeking a peaceful voyage to sleep, these tales of the universe await. If you find yourself drawn to these cosmic voyages, please give this video a thumbs up and subscribe to join our community of fellow space dreamers. And here's something fun. In the comments below, tell me which celestial object you'd most like to visit in a dream. I love hearing where your imagination takes you among the stars. And on that note, let's begin with the cosmic journey of your atoms. In the beginning, there was simplicity. The universe, just minutes after the Big Bang, contained only the lightest elements. Hydrogen made up about 75% of all matter, helium comprised nearly all the rest, and there were tiny traces of lithium. That's it. No carbon, no oxygen, no nitrogen, no iron. None of the elements that would later become essential for planets, for water, for life itself. Think of the early universe like a cosmic kitchen with only 3 ingredients. Imagine trying to bake a cake with just flour, water, and a pinch of salt. You simply can't create the complex, rich flavors that make a cake delicious. The universe faced the same limitation. To create planets, oceans, and eventually life, it needed a much more diverse pantry of elements. The solution came in the form of the first generation of stars. These ancient giants were massive beyond comprehension, some containing hundreds of times more matter than our sun. When gravity pulled together these primordial gas clouds, something magical began to happen. As the hydrogen and helium collapsed inward, the temperature at the core climbed higher and higher. At around 10 million degrees Celsius, hydrogen nuclei moving at incredible speeds began to overcome their natural repulsion and fuse together. This process, called nuclear fusion, released enormous amounts of energy. The star began to shine, and in doing so, it started the first great cosmic recipe for creating heavier elements. Inside these stellar furnaces, hydrogen fused into helium, helium fused into carbon, carbon into oxygen, oxygen into silicon, and so on up the periodic table. Each step required higher temperatures and pressures. The star was like a master chef, slowly building more complex dishes by combining simpler ingredients under increasingly extreme conditions. But these first-generation stars, the ones astronomers call population 3 stars, faced a fundamental limit. When they tried to create elements heavier than iron, the fusion process began to consume energy rather than produce it. Iron became the endpoint, the element that essentially poisoned the fusion process. Picture a star as a constant battle between two forces. Gravity pulls everything inward, trying to collapse the star. The energy from fusion pushes outward, keeping the star inflated like a balloon. For millions of years, these forces balance perfectly. But when iron builds up in the core, fusion can no longer provide the outward pressure needed to fight gravity. The result is catastrophic and beautiful. In less than a second, the core collapses. The outer layers of the star crash inward at thousands of kilometers per second, then rebound in a spectacular explosion called a supernova. These explosions are so bright they can outshine entire galaxies for weeks. But here's the truly remarkable part. In those final moments of collapse and explosion, the extreme conditions finally become powerful enough to forge the heaviest elements. The gold in your jewelry, the silver in your coins, the uranium in nuclear reactors, all of these were created in the death throes of ancient stars. These stellar explosions scattered their newly forged elements across vast distances, seeding space with the building blocks for future generations of stars and planets. The universe's pantry was finally being stocked with all the ingredients necessary for complexity, for planets, and eventually, for you. The death of those first-generation stars was not an ending, but a beginning. Their explosive final moments sent shockwaves rippling through space, carrying with them the precious cargo of heavy elements forged in their cores. These stellar winds traveled for thousands of years, mixing the new elements with the vast clouds of hydrogen and helium that drifted between the stars. Imagine space as an enormous ocean, and these expanding bubbles of stellar debris as drops of ink spreading slowly through the water. Over millions of years, these drops mixed and blended, creating regions of space enriched with carbon, oxygen, silicon, iron, and dozens of other elements. These enriched regions became the stellar nurseries where the next generation of stars would be born. When gravity began to pull together these element-rich gas clouds, something different happened. The new stars that formed were not just hydrogen and helium giants like their predecessors. They contained the full palette of elements, and this made all the difference. These second and third generation stars could form planets, and those planets could have solid surfaces, atmospheres, and eventually, the chemistry necessary for life. Our Sun is one of these later generation stars, born about 4.6 billion years ago from a collapsing cloud that astronomers call the solar nebula. This nebula contained not just hydrogen and helium, but also carbon from ancient supernovas, oxygen from stellar fusion, silicon from dying stars, and iron from cosmic explosions that happened billions of years before our solar system even existed. As the solar nebula collapsed, it began to spin faster, flattening into a disc shaped like pizza dough being spun by a chef. At the center, where most of the mass concentrated, our Sun ignited. But in the cooler outer regions of the disk, something extraordinary was happening. The heavy elements were beginning to stick together. Think of this process like making a snowball. First, tiny particles of dust, made from elements forged in ancient stars, began to clump together through electrostatic forces. These clumps attracted more particles, growing larger and larger. As they grew, their gravity became strong enough to pull in even more material. The temperature in different parts of the solar system determined which elements could condense into solid form. Close to the Sun, where temperatures were scorching, only the most heat-resistant materials like iron and nickel could solidify. This is why the inner planets, including Earth, are rocky worlds with metallic cores. Further from the Sun, where temperatures were cooler, water could freeze into ice, and lighter elements could condense. This is why the outer planets became gas giants, capturing vast amounts of hydrogen and helium, while their moons became icy worlds rich in frozen water and other compounds. During this period of planetary formation, the solar system was a chaotic place. Planetesimals, ranging in size from pebbles to small moons, crashed into each other constantly. Each collision either built up the growing planets or shattered apart, redistributing material throughout the system. Earth formed through this violent process of accretion. Every impact delivered atoms forged in stellar cores billions of years ago. The iron that sank to form our planet's core came from supernova explosions. The silicon and oxygen that formed our rocky mantle were created in the fusion furnaces of dying stars. The carbon that would later become essential for life was manufactured in stellar interiors through a process discovered by astronomer Fred Hoyle. But the story doesn't end with planetary formation. Even after Earth had mostly solidified, impacts continued. Comets and asteroids, themselves made from stellar debris, crashed into our young planet. These impacts delivered water to our oceans and organic compounds that would later participate in the chemistry of life. Every atom in these cosmic visitors had its own stellar origin story, adding new chapters to Earth's growing library of elements. During Earth's first billion years, the atoms that now make up your body were scattered across our planet. Some were dissolved in the primordial oceans, others were locked in rocks and minerals, still others drifted in our early atmosphere. They waited patiently, these stellar children, for the next chapter in their cosmic journey. For nearly a billion years after Earth's formation, our planet was a world in transition. The stellar atoms delivered by cosmic impacts were slowly reorganizing themselves. Driven by the planet's internal heat and the energy from our young Sunday volcanoes brought elements from deep within the Earth to the surface. Rain and rivers carried dissolved minerals from rocks to the oceans. Lightning and ultraviolet radiation provided energy for the first chemical reactions that would eventually lead to life. Think of early Earth as a vast laboratory where stellar atoms were experimenting with new combinations. The carbon atoms forged in dying stars began linking together in chains and rings. Oxygen atoms, created in stellar fusion, combined with hydrogen to form water molecules that filled our growing oceans. Phosphorus atoms, rare products of stellar nucleosynthesis, became part of energy-storing compounds. In this cosmic laboratory, something extraordinary began to happen around 3.8 billion years ago. The stellar atoms started forming increasingly complex partnerships. Carbon, with its unique ability to form 4 chemical bonds, became the backbone of organic molecules. It partnered with hydrogen, oxygen, nitrogen, sulfur, and phosphorus to create amino acids, the building blocks of proteins. These weren't random combinations. The chemical properties of each element, determined by the number of protons in their nuclei, made certain partnerships more favorable than others. Carbon's versatility came from its nuclear structure, created billions of years earlier in stellar cores through the triple alpha process. Nitrogen's ability to form strong bonds was a gift from ancient supernovas. Each element brought its stellar heritage to Earth's growing molecular complexity. The first major breakthrough came when these organic molecules learned to make copies of themselves. RNA molecules, built from stellar carbon, nitrogen, oxygen, and phosphorus, developed the ability to reproduce. This was the moment when chemistry became biology, when stellar atoms transitioned from passive participants to active agents in their own organization. Picture this process like a vast construction site where the building materials suddenly learn to assemble themselves. The calcium atoms, forged in stellar cores, knew how to build structural frameworks. The iron atoms, products of stellar fusion, discovered they could carry oxygen efficiently. The magnesium atoms, gifts from ancient supernovas, found they could help molecules capture and store energy from sunlight. The first simple cells appeared around 3.5 billion years ago. These primitive organisms were little more than bags of water containing concentrated solutions of stellar atoms organized into living systems. But they represented a profound transition. For the first time in cosmic history, stellar atoms were not just reacting to their environment, they were actively changing it. The most important change came when cyanobacteria evolved the ability to perform photosynthesis. Using energy from sunlight, these organisms began splitting water molecules and releasing oxygen gas. This oxygen, made from atoms forged in stellar cores billions of years earlier, began accumulating in Earth's atmosphere for the first time. This period, called the Great Oxidation Event, was actually an environmental catastrophe for most early life forms. Oxygen was toxic to the anaerobic organisms that had dominated early Earth. But this crisis created opportunities for new forms of life that could harness oxygen's chemical power. The stellar iron atoms found new purpose in this oxygen-rich world. Instead of rusting uselessly, they became part of hemoglobin molecules that could bind oxygen reversibly. The stellar carbon atoms discovered they could form more complex partnerships in the presence of oxygen, creating sophisticated organic molecules that stored more energy. Over hundreds of millions of years, the stellar atoms that had been randomly scattered across early Earth became organized into increasingly complex biological systems. They formed the first complex cells, with specialized compartments and sophisticated molecular machinery. They assembled into the first multicellular organisms, creating new levels of organization and cooperation. Each step in this biological evolution was guided by the fundamental properties of stellar atoms. The phosphorus atoms, rare products of stellar nucleosynthesis, became essential components of DNA and RNA. The sulfur atoms, created in stellar cores, formed bridges that gave proteins their complex three-dimensional shapes. The calcium atoms, forged in ancient supernovas, became the building blocks of shells, bones, and cellular communication systems. By the time complex life emerged, Earth had become a living planet where stellar atoms had learned to organize themselves into systems capable of growth, reproduction, and evolution. The atoms in your body had found their calling, transitioning from cosmic wanderers to active participants in the grand experiment of life. As life flourished and diversified over billions of years, the stellar atoms that would eventually become part of you began an intricate dance through Earth's biosphere. They cycled through countless organisms, each one adding new chapters to their biological story. The carbon atom that now sits in your DNA might have once been part of a trilobite scuttling across ancient seafloors, a fern in a carboniferous forest, or a dinosaur roaming Mesozoic landscapes. This great recycling system, powered by the energy of our stellar-born sun, created what scientists call biogeochemical cycles. Think of these cycles as cosmic conveyor belts that move stellar atoms between living organisms, the atmosphere, the oceans, and the rocks beneath our feet. Nothing is ever truly lost, only transformed and relocated. Consider the oxygen atoms you're breathing right now. Some of them were released by prehistoric algae floating in ancient seas. Others were produced by the first land plants as they colonized the continents 400 million years ago. Still others came from the photosynthetic activity of tropical rainforests, grasslands, and marine phytoplankton. Each breath you take connects you to billions of years of biological history. The water molecules in your cells tell equally remarkable stories. The hydrogen atoms in that water are primordial, dating back to the first minutes after the Big Bang. but the oxygen atoms were forged in stellar cores and delivered to Earth through cosmic impacts. Together, these stellar and primordial atoms formed the water molecules that became Earth's oceans, fell as rain, flowed in rivers, and eventually found their way into the biological systems that preceded you. Your calcium atoms have been particularly well traveled. Before becoming part of your bones and teeth, they may have formed the shells of ancient marine organisms, the limestone cliffs of long-vanished coastlines, or the coral reefs that once teemed with prehistoric life. Each calcium atom carries within its nuclear structure the signature of the stellar explosion that created it, billions of years before Earth even existed. The iron atoms in your blood have their own epic journey. Created in the final moments of stellar collapse, they traveled through space for eons before being incorporated into Earth's formation. They may have spent millions of years locked in iron ore deposits, been extracted and forged into tools by early humans, rusted and returned to the soil, been absorbed by plants, consumed by animals, and finally found their way into your hemoglobin molecules. This biological recycling system reached new levels of complexity with the evolution of ecosystems. Stellar atoms began moving through food webs, passing from photosynthetic organisms to herbivores to carnivores and back again. The nitrogen atoms in your proteins may have been fixed from the atmosphere by bacteria and soil, absorbed by plants, consumed by animals, returned to the earth through decomposition, and begun the cycle again countless times. During the Cambrian explosion 540 million years ago, life discovered new ways to organize stellar atoms. The first organisms with hard shells and skeletons created new reservoirs for calcium and phosphorus. The evolution of more complex nervous systems found new uses for sodium and potassium atoms in electrical signaling. Each evolutionary innovation was essentially a new experiment in organizing stellar matter. The emergence of photosynthetic organisms created a fundamental partnership between stellar atoms and stellar energy. Plants learned to capture photons from our sun and use that energy to build complex organic molecules from simple atmospheric components. This process created the first direct connection between our star's energy and the organization of stellar atoms into biological structures. As life moved onto land, stellar atoms found new environments and opportunities. The phosphorus atoms essential for DNA and cellular energy systems became concentrated in soil and rock formations. The sulfur atoms crucial for protein structure cycled through atmospheric gases, ocean currents, and terrestrial ecosystems. Each element developed its own complex pathways through the biosphere. The most recent chapter in this story began with the evolution of humans and our ancestors. For millions of years, your stellar atoms passed through human lineages, creating the genetic heritage that eventually led to you. The DNA molecules carrying your family's genetic information are built from stellar carbon, nitrogen, oxygen, and phosphorus that have been passed down through countless generations. But the stellar atoms in your body aren't just inherited from your parents. Throughout your lifetime, you're constantly exchanging atoms with your environment. The proteins in your muscles are rebuilt every few months using new amino acids constructed from stellar atoms in your food. Your bones are continuously remodeled using calcium atoms that may have recently been part of other organisms or geological formations. Here you are, a walking, thinking collection of stellar atoms that have journeyed across billions of years and countless cosmic environments to come together in this moment. Every carbon atom in your body was forged in the nuclear furnace of a dying star. Every oxygen atom was created through stellar fusion and delivered to Earth through ancient cosmic collisions. Every calcium atom in your bones was born in a supernova explosion that lit up the cosmos billions of years before our solar system existed. Think about the extraordinary odds of this assembly. The atoms that make up your left hand may have traveled completely different paths through space and time before meeting inside you. Some may have spent millions of years locked in sedimentary rocks, others dissolved in ancient oceans, still others cycling through countless organisms across geological time periods. Yet here they are, cooperating in the complex chemistry that allows you to think, feel, and experience the universe. Your body contains approximately 7 octillion atoms. That's a 7 followed by 27 zeros. Each one has its own stellar origin story. The phosphorus atoms in your DNA were created in the cores of massive stars and scattered through space by supernova explosions. They may have drifted through interstellar space for billions of years before being incorporated into the solar nebula that formed our solar system. The magnesium atoms in your muscles, essential for energy production and protein synthesis, were forged through nuclear fusion in stellar interiors. They participated in the cosmic recycling that created our solar system, became part of Earth's rocky material, cycled through geological and biological processes, and finally assembled into the molecular machinery that powers your daily activities. Even the trace elements in your body tell remarkable stories. The zinc atoms crucial for your immune system and wound healing were created through stellar nucleosynthesis. The copper atoms that help transport oxygen in your bloodstream were manufactured in stellar cores. The iodine atoms essential for your thyroid function were produced in the explosive deaths of massive stars. But perhaps most remarkably, you are not a fixed collection of stellar atoms. Your body is in constant flux, exchanging material with your environment. Scientists estimate that you replace most of the atoms in your body within about 7 years. The atoms that composed you as a child are now scattered throughout the biosphere, while new stellar atoms have taken their place. This means you're more like a temporary pattern that stellar atoms form as they flow through the universe. Like a whirlpool in a river, you maintain your structure and identity even as the material that makes you up is constantly changing. You are a dynamic constellation of stellar matter, organized into the extraordinary phenomenon we call life. The hydrogen atoms in your body water connect you directly to the Big Bang itself. These atoms are among the oldest in the universe, created in the first few minutes after the cosmos began. They've witnessed the entire history of the universe, from the formation of the first stars to the evolution of galaxies, the birth of our solar system, and the emergence of life on Earth. When you look up at the night sky, you're not just observing distant stars. You're seeing the nuclear furnaces where your atoms were forged. The light reaching your eyes was created by the same fusion processes that manufactured the carbon in your muscles, the oxygen in your lungs, and the iron in your blood. You are literally made of star stuff, connected to the cosmos in the most fundamental way possible. This stellar heritage makes every human being a walking piece of cosmic history. The atoms in your body have experienced temperatures of millions of degrees in stellar cores, the vacuum of interstellar space, the violence of planetary formation, and billions of years of geological and biological evolution. They carry within them the entire story of our universe's development from simple hydrogen and helium to complex, self-aware beings. And on that note, we complete our cosmic journey through deep time and space, following the remarkable story of stellar atoms as they traveled from ancient dying stars to become the very substance of your being. From the nuclear furnaces of the first generation of stars, through the formation of our solar system, the evolution of Earth's biosphere, and the long chain of life that led to you, every atom in your body carries the history of the universe itself. The next time you look at your hand, remember that you're seeing stellar material that was forged in cosmic fires billions of years ago. When you breathe, You're inhaling atoms that once drifted through the vast emptiness between stars. When your heart beats, it's pumping blood filled with iron created in supernova explosions that outshone entire galaxies. You are not separate from the cosmos. You are the cosmos, temporarily organized into a form capable of contemplating its own existence. The stellar atoms that compose you will continue their cosmic journey long after your brief moment of self-awareness has passed, perhaps becoming part of future organisms on distant worlds, continuing the universe's long experiment with complexity and consciousness. To understand gravitational waves, we must first grasp the nature of spacetime itself. Imagine the universe not as empty void, but as a flexible, invisible fabric stretching in all directions. This fabric, which Einstein called spacetime, is the stage upon which all cosmic drama unfolds. Every star, planet, and galaxy sits upon this fabric like bowling balls resting on a stretched rubber sheet. When Albert Einstein published his theory of general relativity in 1915, he revealed that massive objects actually bend this cosmic fabric. Picture dropping a heavy marble onto a trampoline. The marble creates a depression, curving the surface around it. Similarly, the sun creates a depression in spacetime, and Earth follows the curved path around this depression, which we experience as orbital motion. Einstein's equations predicted something remarkable. When massive objects accelerate through space, they should create ripples in this fabric, much like a stone thrown into a still pond creates expanding circles of waves. These ripples, moving at the speed of light, would carry information about their source across the cosmos. For decades, these gravitational waves remained purely theoretical. The ripples are incredibly subtle, stretching and compressing space by amounts smaller than a proton's width across distances of several kilometers. Einstein himself doubted whether such tiny distortions could ever be detected. The waves are so gentle that they pass through Earth, through our bodies, through everything, barely interacting with matter at all. Yet these invisible messengers carry profound information. Unlike light, which can be absorbed or scattered, gravitational waves travel unimpeded from their source. They offer us a completely new way to observe the universe, like developing a new sense after being born with only 4. Where optical telescopes show us the universe painted in light, gravitational wave detectors allow us to feel the universe's rhythm, sensing the cosmic heartbeat of colliding giants in distant galaxies. The sources of these waves are among the most extreme environments in the cosmos, pairs of black holes spiraling toward each other, neutron stars colliding in brilliant explosions, and possibly even echoes from the universe's first moments after the Big Bang. Each event creates its own unique signature in the fabric of spacetime, a fingerprint written in geometry itself. In the vast darkness between galaxies, some of the universe's most spectacular dances unfold in complete silence. Picture 2 black holes, each containing the mass of dozens of suns compressed into regions smaller than cities, locked in an eternal gravitational embrace. These cosmic partners orbit each other in an accelerating spiral, their immense gravity gradually drawing them closer together over millions of years. As these black holes orbit, they act like cosmic violins, their motion generating gravitational waves that ripple outward through spacetime. Initially, when the black holes are far apart, they create long, slow waves, like the deep bass notes of a cosmic orchestra. The waves carry away energy from the system, causing the orbit to decay ever so slowly. But as the black holes draw closer, something magnificent happens. Their orbital speed increases, following the same principle that makes a figure skater spin faster when pulling in their arms. The gravitational waves grow stronger and more frequent, like a musical pitch rising higher and higher. What began as a barely perceptible bass note gradually becomes a cosmic crescendo. In the final moments before collision, the black holes reach incredible speeds, sometimes circling each other hundreds of times per second. The spacetime around them becomes a turbulent sea of gravitational waves. These final seconds, called the inspiral phase, create waves so powerful they can be detected by instruments on Earth, even when the collision occurred billions of light years away. The actual merger happens almost instantaneously. Two separate black holes become one larger black hole in a fraction of a second. This moment, called the chirp, creates the loudest gravitational wave signal. The newly formed black hole wobbles briefly, like a struck bell, before settling into a stable configuration. This final ringing phase, appropriately called the ring down, gradually fades as the system returns to equilibrium. What makes these events truly extraordinary is their energy output. In those final moments of merger, the collision converts several solar masses worth of matter directly into gravitational wave energy, following Einstein's famous equation E=mc². For a brief moment, these distant collisions shine brighter in gravitational waves than all the stars in the observable universe shine in visible light. Scientists have now detected dozens of these black hole mergers, each one telling a unique story. Some involve black holes of similar mass, creating symmetric spirals. Others feature mismatched pairs, where a larger black hole gradually consumes a smaller companion. Each collision adds another note to our growing understanding of the universe's gravitational symphony. While black hole collisions create the universe's deepest bass notes, neutron-star mergers contribute their own unique voice to the cosmic symphony. Neutron stars are among the most exotic objects in the universe, the collapsed cores of massive stars, containing the mass of our sun compressed into a sphere only 20 kilometers across. A teaspoon of neutron star material would weigh as much as Mount Everest. These stellar remnants are incredibly dense and perfectly spherical, spinning like cosmic tops at rates that can exceed 700 rotations per second. Their surfaces are smoother than any human-made object, yet their magnetic fields are trillions of times stronger than Earth's. When two of these extreme objects orbit each other, they create gravitational waves with distinctly different characteristics than black hole mergers. Neutron star binaries spiral inward more gradually than black holes, their smaller size allowing them to orbit much closer before merging. This creates gravitational wave signals that last longer, sometimes detectable for minutes before the final collision. The waves gradually increase in frequency and amplitude, like a cosmic siren approaching from the depths of space. But neutron-star collisions offer something that black hole mergers cannot, a spectacular light show. Unlike black holes, which trap all electromagnetic radiation, neutron stars can produce brilliant explosions visible across the electromagnetic spectrum. When two neutron stars finally touch, the collision creates what astronomers call a kilonova, an explosion that outshines entire galaxies. These cosmic fireworks serve a profound purpose in the universe's economy. The extreme conditions during neutron-star mergers forge heavy elements that cannot be created any other way. Gold, platinum, uranium, and other elements heavier than iron are born in these stellar furnaces. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, all were forged in neutron-star collisions billions of years ago and scattered across space to eventually become part of planets and life. The gravitational waves from neutron-star mergers carry detailed information about these exotic objects. By analyzing the wave patterns, scientists can measure the stars' masses, determine their internal structure, and even constrain the behavior of matter under the most extreme conditions possible. Each detected merger provides new insights into the fundamental physics governing these cosmic laboratories. The combination of gravitational waves and traditional electromagnetic observations creates what scientists call multi-messenger astronomy. Instead of relying on light alone, we can now correlate gravitational wave detections with optical, radio, X-ray, and gamma-ray observations of the same event. This provides a far richer understanding of these cosmic phenomena than either approach could achieve alone. Detecting gravitational waves requires some of the most sensitive scientific instruments ever built. The challenge is immense, measuring changes in distance smaller than 1/10,000th the width of a proton across baselines several kilometers long. It's equivalent to measuring the distance from Earth to the nearest star with precision better than the width of a human hair. The solution came in the form of laser interferometry, a technique that uses the wave nature of light to detect incredibly small changes in distance. Picture an L-shaped building with arms stretching 4 kilometers in perpendicular directions. Laser light travels down each arm, reflects off mirrors, and returns to a detector where the beams are combined. Under normal conditions, the two beams arrive perfectly synchronized, canceling each other out in a phenomenon called destructive interference. But when a gravitational wave passes through the detector, it stretches space in one direction while compressing it in the perpendicular direction. This changes the travel time for light in each arm by slightly different amounts, causing the laser beams to arrive slightly out of synchronization. The resulting interference pattern reveals the passage of the gravitational wave with extraordinary precision. The Laser Interferometer Gravitational Wave Observatory consists of two identical detectors located 3,000 kilometers apart in Louisiana and Washington state. This separation is crucial for confirming detections and determining the direction from which waves arrive. A true gravitational wave signal will appear at both detectors with a time delay corresponding to the wave's travel time between sites. Building these instruments required solving countless technical challenges. The mirrors must be isolated from all vibrations, suspended by sophisticated systems that filter out everything from earthquakes to traffic passing nearby. The laser systems must maintain incredible stability, and the entire apparatus operates in ultra-high vacuum to prevent air molecules from interfering with the light beams. The detectors are so sensitive they can measure disturbances from ocean waves crashing on distant shores, storms thousands of kilometers away, and even the quiet footsteps of researchers walking near the facility. Sophisticated algorithms help distinguish true gravitational wave signals from this constant background of terrestrial noise. Europe operates its own detector called Virgo in Italy, and additional detectors are planned or under construction in Japan and India. This growing network will provide better sky localization and more detailed studies of gravitational wave sources. Each additional detector improves our ability to triangulate the position of cosmic collisions and alert other telescopes to observe the aftermath. The detection of gravitational waves has opened an entirely new window on the universe, revealing cosmic phenomena that remain invisible to traditional telescopes. In the few years since the first detection in 2015, these cosmic messengers have already revolutionized our understanding of black holes, neutron stars, and the fundamental nature of gravity itself. Before gravitational wave astronomy, our knowledge of black holes came primarily from observing their effects on nearby matter. We could infer their presence by watching stars orbit invisible companions or by observing matter spiraling into accretion disks. But gravitational waves allow us to observe black holes directly, measuring their masses and spins with unprecedented precision. The universe revealed by gravitational waves is more dynamic and violent than we ever imagined. Black hole mergers occur far more frequently than predicted, suggesting that these cosmic collisions have been shaping galactic evolution throughout cosmic history. The detected black holes often have masses larger than expected, challenging our models of stellar evolution and collapse. Neutron star mergers have solved long-standing mysteries about the origin of heavy elements. For decades, astronomers debated whether these elements were created in supernovae or through other processes. Gravitational wave detections of neutron star collisions, combined with optical observations of the resulting kilonovae, have confirmed that these mergers are indeed cosmic forges where gold and platinum are born. Future gravitational wave detectors will be even more sensitive, capable of detecting smaller mergers and more distant events. Space-based detectors like the planned LISA mission will observe different types of sources entirely, including massive black holes at the centers of galaxies and potentially even primordial gravitational waves from the Big Bang itself. These cosmic ripples carry information about some of the most extreme physics in the universe, the behavior of matter at nuclear densities, the properties of spacetime near black holes, and the fundamental nature of gravity itself. Each detection provides a new laboratory for testing Einstein's theory under conditions impossible to replicate on Earth. Perhaps most remarkably, gravitational waves offer the possibility of observing the very early universe directly. Unlike light, which was trapped in hot, opaque plasma for the first 380,000 years after the Big Bang, gravitational waves could have traveled freely from the universe's first moments. Future detectors might glimpse the cosmic dark age before the first stars formed. And on that note, we conclude our gentle exploration of the universe's silent symphony. We've journeyed from the fundamental nature of spacetime itself to the incredible instruments that allow us to feel the cosmic heartbeat of colliding giants. These gravitational waves, rippling through the fabric of reality at the speed of light, carry stories from the most extreme environments in the cosmos, whispering secrets about black holes, neutron stars, and the very nature of existence itself. As we drift towards sleep, consider the profound beauty of this cosmic orchestra that plays constantly around us. Every moment, gravitational waves from countless collisions throughout the universe wash over our planet like gentle tides in an invisible ocean. These waves began their journey billions of years ago, when our solar system was nothing more than a cloud of dust and gas. They have traveled across the vast emptiness of space, carrying their messages through the cosmic dark ages, past the formation of the first stars, through the birth and death of countless galaxies. The universe speaks to us in frequencies far below human hearing, in wavelengths longer than continents, and amplitudes smaller than atomic nuclei. Yet through the ingenuity of human science, we have learned to listen to these cosmic whispers. Each detection is like catching a single snowflake from a blizzard that has been falling since the dawn of time. The gravitational waves we detect today represent just the loudest voices in this cosmic choir, the most dramatic collisions in our cosmic neighborhood. In the coming years, as our detectors become more sensitive and new instruments join the global network, we will hear fainter and more distant voices in this gravitational symphony. We may detect the gentle hum of white dwarf stars orbiting each other in our own galaxy, the thunderous roar of supermassive black holes merging at the hearts of distant galaxies, or perhaps even the primordial echoes from cosmic inflation itself. Each new detection will add another instrument to our cosmic orchestra, revealing harmonies we never knew existed. The universe continues its eternal dance among the stars, weaving spacetime into patterns of breathtaking complexity and beauty. Black holes spiral toward their inevitable embrace, neutron stars waltz through space in perfectly choreographed orbits, and somewhere in the distance, new cosmic collisions are creating the gravitational waves that will reach Earth long after we are gone. This is the universe's most patient art form, composing symphonies that play across billions of years, painting with the very fabric of reality itself. To understand the cosmic web, we must first travel back to when the universe was merely 380,000 years old, a cosmic infant by today's standards. At this moment, known as recombination, the universe had cooled enough for the first atoms to form, creating what astronomers call the cosmic microwave background. But hidden within this seemingly smooth afterglow were tiny temperature variations, quantum fluctuations from the Big Bang that would eventually grow into the largest structures we observe today. Think of these early fluctuations like seeds scattered across a vast cosmic garden. Each seed represented a slightly denser region of matter, primarily dark matter, that would begin attracting more material through gravitational pull. Over millions of years, these seeds grew, drawing in surrounding matter like cosmic vacuum cleaners, creating an increasingly complex network of filaments and nodes that would define the universe's architecture for billions of years to come. The cosmic web emerges naturally from the interplay between dark matter's gravitational attraction and the universe's expansion. Over these tens of millions of years, the dark matter assembled into a complex network of intersecting filaments called the cosmic web. Picture how soap bubbles form when you blow them through a bubble wand, creating thin films that connect at various junctions while leaving empty spaces between them. The cosmic web forms similarly, with matter flowing along preferred paths while leaving vast voids relatively empty. These massive, thread-like formations can commonly reach 50 to 80 megaparsecs, with the largest found to date being Kipu, at 400 megaparsecs, stretching distances that dwarf even our local group of galaxies. To visualize this scale, imagine the Milky Way as a grain of sand. A typical cosmic filament would stretch from New York to Los Angeles, while the largest known filament, Kipu, would span from Earth to the Moon and back again 16 times. What makes these filaments particularly fascinating is their composition. Dark matter's dominance over everyday matter also means it dominates the filaments of the cosmic web, forming an invisible scaffold along which the universe's structure takes shape. Dark matter, that mysterious substance that doesn't interact with light but comprises most of the universe's mass, creates the invisible highways that guide normal matter, the kind that makes up stars, planets, and ourselves along predetermined paths. The formation process resembles how rivers carve valleys through landscapes over geological time. Just as water naturally flows along paths of least resistance, creating networks of tributaries and main channels, matter in the early universe followed the gravitational landscape created by dark matter, flowing along filaments toward the deepest gravitational wells that would become galaxy clusters. These pathways don't exist in isolation. These filaments and sheets are separated by cosmic voids, vast empty regions that contain very little matter. The relationship between filaments and voids is symbiotic, each defining the other. Filaments exist because matter has been drained from the voids, while voids exist because their matter has flowed into the surrounding filaments. Computer simulations reveal the web's intricate beauty. When astronomers modeled the universe's evolution using supercomputers, dark matter clumped into blobs along narrow filaments with superclusters of galaxies forming a cosmic web at scales on which entire galaxies appear like tiny particles. These simulations show a universe that looks remarkably similar to neural networks in biological systems, suggesting fundamental organizational principles that operate across vastly different scales. The cosmic web's influence extends far beyond its role as cosmic architecture. It actively shapes galaxy formation and evolution, determining where star formation occurs and how galaxies interact with their environment. Galaxies born along filaments experience different evolutionary paths than those in voids, receiving steady streams of fresh gas that fuel continued star formation like cosmic feeding tubes. As we drift through our minds along these invisible highways tonight, consider how the cosmic web represents the universe's attempt to organize itself. From quantum chaos comes cosmic order. From microscopic fluctuations emerge structures visible across billions of light years. The filaments we're exploring represent nothing less than the universe's skeletal system, the hidden framework that supports everything we can see and touch. Mapping something invisible presents unique challenges, like trying to chart ocean currents by watching floating debris or detecting wind patterns by observing how leaves dance through the air. The cosmic web, composed primarily of dark matter that neither emits nor absorbs light, requires similarly indirect methods of detection. Astronomers have become cosmic detectives, piecing together evidence from multiple sources to reveal the universe's hidden scaffold. The most obvious clues come from galaxies themselves. Each bright knot is an entire galaxy, while the purple filaments show where material exists between the galaxies. To the human eye, only the galaxies would be visible, and this visualization allows us to see the strands of material connecting the galaxies and forming the cosmic web. When astronomers map galaxy positions across vast regions of space, they discover that galaxies aren't randomly scattered like stars across Earth's night sky. Instead, they form chains and clusters connected by seemingly empty regions, outlining the underlying dark matter structure like Christmas lights strung along invisible wires. Large-scale galaxy surveys have revolutionized our understanding of cosmic structure. Projects that map millions of galaxies reveal a network of filamentary structures that are analogous to the cosmic web seen in numerical simulations. These surveys show that galaxies trace out the same web-like patterns that computer simulations predict, providing strong evidence that our theoretical understanding matches cosmic reality. But galaxies represent only the tip of the iceberg. The real breakthrough came when astronomers learned to detect the gravitational effects of dark matter filaments. Just as a massive object bends the fabric of spacetime, causing light to curve around it, dark matter filaments create subtle gravitational lensing effects that distort the shapes of background galaxies. Think of looking through a bathroom window with textured glass, where the imperfections slightly bend and distort the view beyond. Dark matter filaments create similar distortions, though much more subtle, that require sophisticated analysis to detect. Recent technological advances have enabled direct observations of filament material. After hundreds of hours of observations, an international team of researchers has captured the sharpest ever image of one of these cosmic filaments. These breakthrough observations reveal not just the dark matter scaffold, but also the normal matter, primarily hydrogen gas, that flows along these cosmic highways. Scientists have also discovered ways to detect dark matter filaments using gravitational effects on surrounding galaxies. These are filaments that sit isolated between galaxies in the largest and most hidden portions of the cosmic web. Advanced telescopes and analysis techniques now allow astronomers to measure how the gravity of these invisible structures affects the motion and distribution of nearby galaxies, much like detecting an underground river by observing how surface vegetation grows in patterns above it. The cosmic web reveals itself through temperature signatures as well. Gas flowing along filaments heats up due to compression and gravitational interactions, creating detectable X-ray emissions. Space-based X-ray telescopes can sometimes spot these hot gas trails, revealing the pathways that normal matter follows as it flows along dark matter filaments toward galaxy clusters. Radio telescopes contribute another piece of the puzzle. Astronomers think that cold, dark filaments in deep space snake their way to the galaxies, supplying them with gas, which is fuel for making more stars. Radio observations can detect hydrogen gas in these cold filaments, revealing the fuel supply lines that keep galaxies actively forming new stars. Computer simulations play a crucial role in cosmic web detection. Astronomers create detailed models of how the universe should evolve from initial quantum fluctuations to the present day, then compare these predictions with actual observations. The size of the simulation is a cube with a side length of 134 megaparsecs, or 437 million light-years, allowing researchers to model cosmic web formation across vast scales and verify their theoretical understanding. The most remarkable aspect of cosmic web detection is how multiple independent methods all point to the same underlying structure. Galaxy surveys, gravitational lensing, X-ray observations, radio telescope data, and computer simulations all reveal consistent patterns, like different instruments in an orchestra playing the same cosmic symphony. This convergence of evidence gives astronomers confidence that their maps of the cosmic web accurately reflect the universe's hidden architecture. As we continue our journey along these invisible highways, we begin to appreciate how human ingenuity can reveal the universe's most hidden secrets through careful observation, clever analysis, and patient detective work spanning decades of research. Imagine cosmic rivers flowing through the darkness of space, carrying the raw materials that fuel star formation in galaxies throughout the universe. These aren't rivers of water, but streams of hydrogen gas flowing along dark matter filaments like nutrients through cosmic arteries. Tonight we'll follow these celestial waterways as they deliver the essential ingredients for stellar birth to galactic communities scattered across billions of light years. The process begins in the spaces between galaxies, where primordial hydrogen gas, left over from the Big Bang, drifts through the cosmos at temperatures barely above absolute zero. This intergalactic medium contains roughly half of all normal matter in the universe, waiting to be harvested by hungry galaxies through their dark matter filament connections. Dark matter filaments act like cosmic conveyor belts, channeling this diffuse gas toward gravitational gathering points where galaxies form and evolve. The process resembles how tree roots extend through soil, gathering nutrients from wide areas and concentrating them where they're needed most. This steady supply of fresh material allows galaxies to continue forming new generations of stars for billions of years. The gas doesn't flow gently along these cosmic highways. As it moves toward galaxies, gravitational forces compress and accelerate it, heating the material through friction and gravitational interactions. Think of water flowing down a mountainside, starting as a gentle stream but gaining speed and turbulence as it approaches the valley below. This heating process creates observable signatures that astronomers use to trace the flow of cosmic nutrition. Gas heated to millions of degrees emits X-rays, creating faint but detectable trails that reveal the pathways along which galaxies receive their sustenance. The feeding process varies dramatically depending on a galaxy's environment within the cosmic web. Galaxies located at major filament intersections, where multiple cosmic highways converge, receive abundant supplies of fresh gas and tend to be larger, more massive, and more actively forming stars. These cosmic metropolitan areas bustle with activity and growth fueled by their excellent connectivity to the cosmic supply network. In contrast, galaxies dwelling in cosmic voids, far from major filaments, experience cosmic starvation. These isolated island galaxies must survive primarily on their initial gas reservoirs, like desert settlements cut off from major trade routes. They typically show signs of reduced star formation and may eventually exhaust their fuel supplies. The cosmic web's influence extends beyond simply supplying raw materials. The direction from which gas approaches a galaxy affects its rotation, structure, and ultimate evolution. Gas flowing along filaments tends to approach galaxies from preferred directions, creating the spinning disk structures we observe in spiral galaxies like our Milky Way. Recent observations have revealed the intricate details of this cosmic feeding process. Advanced telescopes can now detect the faint signatures of gas flowing along filaments, showing how galaxies actively draw material from their cosmic web connections. Some galaxies experience feeding frenzies when multiple filaments converge, delivering massive amounts of fresh gas simultaneously. These cosmic banquets can trigger bursts of intense star formation, creating the brilliant starburst galaxies that astronomers observe throughout the universe. At the grandest scales of cosmic architecture, filaments don't simply stretch endlessly through space, but converge at magnificent intersections where the universe's largest gravitationally bound structures take shape. These cosmic crossroads, where multiple dark matter highways meet, create the galaxy clusters that serve as the universe's greatest cities, bustling metropolitan centers where thousands of galaxies gather in gravitational harmony. Picture the intersection of major interstate highways during rush hour, but instead of cars, imagine entire galaxies flowing toward a common destination. These clusters, and the elongated chains of galaxies called filaments which connect them, form a highly complex and anisotropic matter distribution at the megaparsec scale called the cosmic web. These intersections represent the most massive structures in the universe, some containing the equivalent mass of millions of billions of suns concentrated in regions spanning several million light years. The formation of these cosmic intersections follows predictable patterns established by the underlying dark matter distribution. Computer simulations show that nodes naturally develop where multiple filaments meet, much like how cities historically grew at river confluences or mountain pass intersections. The gravitational pull of these developing nodes attracts more matter along the connecting filaments, creating a positive feedback loop that grows increasingly massive structures over cosmic time. As we approach one of these intersections in our imagination, the view transforms dramatically. What began as a journey along relatively sparse filaments suddenly opens into a cosmic megalopolis teeming with galactic activity. Instead of the occasional galaxy encountered along isolated filament stretches, cluster cores contain galaxy densities hundreds of times higher than average cosmic density. The night sky from a planet within such a cluster would blaze with the combined light of thousands of neighboring galaxies, creating perpetual cosmic dawn. The environment within these intersections profoundly affects galaxy evolution. Galaxies entering cluster cores experience gravitational interactions with their numerous neighbors, distorting their shapes and sometimes triggering intense bursts of star formation through close encounters. Think of how traffic patterns change when multiple highway lanes merge into a busy intersection, with vehicles forced into closer proximity and more complex interactions. Cluster cores also contain another remarkable feature: vast clouds of extremely hot gas that fill the space between member galaxies. This intracluster medium, heated to temperatures exceeding 100 million degrees Celsius, emits intense X-ray radiation that makes galaxy clusters among the most luminous X-ray sources in the universe. The gas represents material that has been stripped from member galaxies through gravitational interactions and heated through the cluster's immense gravitational well. The hot intracluster gas creates a hostile environment for star formation in member galaxies. As galaxies move through this superhot medium, the pressure strips away their own cooler gas reserves, like strong cosmic winds removing fuel supplies. This process, called ram pressure stripping, transforms gas-rich spiral galaxies into gas-poor elliptical galaxies over hundreds of millions of years, fundamentally altering their ability to form new stars. Despite the harsh cluster environment, these intersections play crucial roles in cosmic evolution. They serve as laboratories where astronomers can study galaxy interactions, dark matter distribution, and the large-scale structure formation process. The extreme conditions found in cluster cores don't exist anywhere else in the universe, making them natural experiments in extreme cosmic physics. Navigation through these cosmic intersections requires understanding their complex gravitational landscapes. Unlike the relatively straightforward gravitational fields along isolated filaments, cluster cores present chaotic gravitational environments where multiple massive galaxies, dark matter concentrations, and gas clouds all contribute to the total gravitational field. This complexity creates fascinating phenomena like gravitational arcs, where the cluster's combined mass bends light from background galaxies into spectacular curved streaks across the cosmic landscape. Some of the universe's most massive galaxy clusters sit at intersections where 6 or more major filaments converge, creating structures so massive they can bend spacetime significantly. These supercluster nodes represent the largest gravitationally bound objects in existence, with masses equivalent to millions of billions of stars concentrated in relatively compact cosmic volumes. The ongoing accretion of matter along filaments ensures that these intersections continue growing throughout cosmic time. Fresh galaxies arrive regularly along the various highways, while streams of intergalactic gas flow toward cluster cores, maintaining these cosmic cities as dynamic, evolving structures rather than static cosmic monuments. As we navigate through these bustling cosmic intersections tonight, we witness the universe's capacity for organization and growth, where the meeting of invisible highways creates visible monuments to gravitational architecture that will endure for cosmic ages. Between the bustling highways of cosmic filaments lie vast territories of almost unimaginable emptiness, the cosmic voids. These immense regions, stretching hundreds of millions of light years across, contain so little matter that a traveler could journey for cosmic ages without encountering a single galaxy. Tonight we drift into these serene cosmic deserts, where the universe reveals its most peaceful and mysterious face. To appreciate the scale of cosmic voids, imagine our local group of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller companions, as a small pebble. A typical cosmic void would be an empty auditorium large enough to hold millions of such pebbles, yet containing only a handful scattered across its vast volume. These filaments and sheets are separated by cosmic voids, vast empty regions that challenge our understanding of how matter organizes itself on the largest scales. The formation of cosmic voids follows naturally from the same processes that create filaments and clusters. In the early universe, regions that started with slightly lower than average density continued to lose matter as cosmic expansion and gravitational attraction drew material toward denser neighboring regions. Over billions of years, this process carved out enormous cavities in the cosmic web, like soap bubbles forming in cosmic foam, each bubble representing a region where matter has been systematically drained away. The emptiness of cosmic voids is almost beyond human comprehension. While the average density of matter in the universe equals roughly 6 protons per cubic meter, the interiors of cosmic voids contain matter densities 1/10 that value or less. To put this in perspective, the best laboratory vacuums on Earth contain trillions of times more particles per unit volume than the emptiest regions of cosmic voids. Yet cosmic voids aren't entirely empty. Careful observations have revealed sparse populations of void galaxies, isolated island universes that formed in these cosmic deserts despite the challenging low-density environment. These void galaxies tend to be smaller, less massive, and more actively forming stars than their counterparts along filaments and in clusters. They represent cosmic pioneers that managed to gather enough material to form galaxies despite their disadvantageous positions in the cosmic web. The few galaxies that do inhabit cosmic voids experience remarkably different evolutionary paths. Without the steady streams of fresh gas that filament-connected galaxies enjoy, void galaxies must rely primarily on their initial material endowments. However, they also avoid the disruptive galaxy interactions and gas stripping processes common in denser environments, allowing them to evolve in relative isolation like cosmic hermits pursuing independent destinies. Void galaxies often display unusual properties that reveal the importance of environment in galaxy evolution. They tend to be bluer than average, indicating active star formation fueled by undisturbed gas reservoirs. They also show less evidence of past galaxy mergers and interactions, preserving more pristine records of how galaxies form and evolve in undisturbed conditions. The boundaries of cosmic voids aren't sharp walls but gradual transitions where density slowly increases toward the surrounding filaments. These void walls, as astronomers call them, contain elongated chains of galaxies that mark the transition zones between void interiors and the denser filament networks. Think of these boundary regions like coastal areas where ocean meets land, creating unique environments that combine characteristics of both domains. Recent discoveries have revealed that cosmic voids possess their own internal structure. Rather than being perfectly spherical empty bubbles, large voids often contain internal subvoids and connecting tunnels that create complex three-dimensional geometries. Some researchers describe this structure as resembling Swiss cheese, with holes of various sizes connected by tunnels and chambers throughout the cosmic volume. The expansion of the universe affects cosmic voids differently than denser regions. While gravity works to slow expansion in areas where galaxies and dark matter concentrate, cosmic voids experience less gravitational braking and expand faster than the overall cosmic average. This differential expansion gradually makes voids larger and emptier over cosmic time, enhancing the contrast between the densest and most sparse regions of the cosmic web. Cosmic voids also provide unique laboratories for testing theories of gravity and dark energy. The behavior of matter and spacetime in these low-density environments can reveal subtle effects that are masked by stronger gravitational influences in denser regions. Some theories predict that modifications to gravity or dark energy properties would be most readily detectable in void environments. As we drift through these cosmic deserts tonight, we experience the universe's capacity for both organization and emptiness, where the absence of matter creates spaces as magnificent and mysterious as the most densely packed galaxy clusters. Our final destination on tonight's journey brings us home to examine our own cosmic neighborhood and the Milky Way's place within the grand architecture we've been exploring. Far from being cosmic wanderers adrift in empty space, our galaxy and its companions occupy a specific address within the cosmic web, connected to the universe's largest structures through the same dark matter filaments that guide galactic evolution throughout the cosmos. The Milky Way resides within what astronomers call the local sheet, a relatively flat distribution of galaxies that forms part of a larger structure called the local supercluster. Our cosmic neighborhood includes the nearby Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller companion galaxies, all gravitationally bound together in what we call the local group. This family of galaxies occupies a region about 10 million light-years across, a modest cosmic suburb compared to the massive galaxy clusters we encountered earlier. But our local group doesn't exist in isolation. We're connected to the broader cosmic web through filamentary structures that stretch toward the Virgo cluster, a massive galaxy cluster containing over 1,300 member galaxies located about 54 million light-years away. Think of the Virgo cluster as our cosmic downtown, a major metropolitan center connected to our suburban neighborhood through cosmic highways of dark matter and sparse galaxy chains. Recent three-dimensional maps of our cosmic vicinity reveal that we occupy a relatively quiet region of the cosmic web. The local group sits near the edge of what's called the local void, a cosmic desert stretching about 150 million light-years across. This positioning explains some characteristics of our galactic neighborhood. We don't experience the intense galaxy interactions common in cluster cores, but we also don't receive the abundant fresh gas supplies that fuel star formation in galaxies along major cosmic filaments. Our location within this cosmic geography has profoundly influenced the Milky Way's evolution and our existence as conscious observers. The relatively peaceful environment has allowed our galaxy to maintain its spiral structure and continue steady star formation for billions of years. Had we formed in a dense cluster core, gravitational interactions might have disrupted our galaxy's delicate spiral arms and stripped away the gas needed for ongoing star formation, potentially preventing the formation of solar systems like our own. The dark matter halo surrounding the Milky Way connects us to larger cosmic web structures through what astronomers call the cosmic web's feeding filaments. These connections continue supplying our galaxy with small amounts of fresh intergalactic gas, maintaining the fuel supply needed for new star formation. Recent observations using radio telescopes have detected streams of hydrogen gas flowing toward our galaxy along these cosmic pathways, confirming that the Milky Way remains actively connected to the cosmic web's supply network. Our position also affects the night sky we observe from Earth. Because we sit relatively close to the local void, we see fewer bright galaxies in certain directions compared to others. The famous Virgo cluster, visible to telescopes in the constellation Virgo, represents our view toward one of the cosmic web's major nodes. In contrast, looking toward the local void reveals far fewer bright galaxies, creating the impression of empty cosmic desert in those directions. The cosmic web's influence extends to our galaxy's satellite companions. The large and small Magellanic Clouds, visible to southern hemisphere observers as fuzzy patches in the night sky, are small galaxies currently falling into the Milky Way along paths determined by the local dark matter distribution. Their orbits and ultimate fate reflect the gravitational environment created by our position within the cosmic web. Looking toward our cosmic future, the cosmic web will continue shaping our galactic destiny. In approximately 4.5 billion years, the Andromeda Galaxy will collide and merge with the Milky Way, an event orchestrated by the gravitational forces operating within our local group. This cosmic collision, which astronomers have dubbed Andromeda, represents our participation in the ongoing evolution of cosmic web structures. Our journey tonight has taken us from the universe's largest structures down to our own cosmic backyard, revealing how we're intimately connected to the cosmos through invisible threads of dark matter that stretch across billions of light years. The same physical processes that create massive galaxy clusters and cosmic voids also determine our galaxy's characteristics and our existence as observers contemplating the cosmic web's magnificent architecture. From our small planet orbiting an ordinary star in an unremarkable spiral arm, we've discovered our place within the universe's grandest structures, finding that even in cosmic terms, we truly belong to a connected, organized, and wondrous cosmic community. And on that note, our peaceful journey through the cosmic web draws to a close. Tonight we've drifted along invisible highways of dark matter that stretch across billions of light years, connecting every galaxy in existence through a magnificent network that rivals the most complex structures found anywhere in nature. We've witnessed how these ethereal filaments channel the raw materials for star formation, creating cosmic rivers that nourish galactic communities throughout the universe. We've navigated through the bustling intersections where cosmic highways converge into the universe's greatest cities, explored the serene emptiness of cosmic voids, and discovered our own place within this grand architecture. The cosmic web reveals a universe that, despite its apparent chaos, possesses an underlying order and connectivity that links the smallest quantum fluctuations to the largest structures we can observe. Before we can understand how time behaves strangely across the universe, we need to establish the groundwork laid by Albert Einstein in 1905 with his special theory of relativity. This revolutionary framework emerged from a simple but profound observation about light. Einstein recognized that the speed of light in a vacuum is constant for all observers, regardless of their motion. This might seem unremarkable at first, but it leads to extraordinary consequences. Think of it like this. Imagine you're on a train throwing a ball forward. To someone standing on the platform, the ball's speed is your throwing speed plus the train's speed. But light doesn't behave this way. Whether you're standing still or racing through space at tremendous velocity, you'll always measure light traveling at exactly 299,792,458 meters per second. This constancy of light speed forced Einstein to a startling conclusion. If the speed of light never changes, then space and time themselves must be flexible. They form what physicists call spacetime, a four-dimensional fabric that can stretch, compress, and bend. When we move through space, we're actually moving through space-time, and this motion affects how we experience time's passage. The faster you move through space, the slower you move through time. This isn't just theoretical speculation. Particle accelerators routinely observe subatomic particles called muons, which normally decay in microseconds, lasting much longer when accelerated to near light speed. Their internal clocks literally run slower from our perspective. Consider two twins. One stays on Earth while the other travels to a distant star at 90% the speed of light. During the journey, the traveling twin experiences time normally from their own perspective. They eat meals, sleep, and think at regular intervals. However, relative to Earth, their biological processes, their clocks, even their thoughts unfold in slow motion. When they return, they find their Earth-bound sibling has aged significantly more. This time dilation effect becomes more pronounced as speeds approach light speed. At 99% of light speed, time passes about 7 times slower for the traveler compared to a stationary observer. At 99.9%, this factor jumps to over 22. The mathematics are precise and unforgiving. Time dilation equals 1 divided by the square root of 1 minus velocity squared divided by light speed squared. GPS satellites orbiting Earth experience this effect daily. They travel at about 14,000 kilometers per hour, causing their onboard clocks to run slightly slower than identical clocks on Earth's surface. Without correcting for this relativistic effect, GPS systems would accumulate errors of several kilometers per day, making navigation impossible. The implications extend far beyond technology. Time dilation reveals that simultaneity, the concept of events happening at the same time, depends entirely on your reference frame. Two events that appear simultaneous to one observer may occur at different times for another observer in motion. This relativity of simultaneity strikes at our deepest intuitions about the nature of time and causality. While motion through space affects time's flow, Einstein's general theory of relativity, published in 1915, revealed an even more surprising truth: gravity itself warps time. This gravitational time dilation occurs because massive objects curve the fabric of spacetime, and time flows more slowly in stronger gravitational fields. Picture spacetime as a stretched rubber sheet. Place a bowling ball in the center, and it creates a depression. Smaller objects placed nearby will roll toward the bowling ball, not because of some mysterious attractive force, but because they're following the curved geometry of the sheet. Similarly, massive objects like stars and planets create curves in spacetime that we experience as gravity. The deeper you are in a gravitational well, the more slowly time passes relative to regions of weaker gravity. On Earth's surface, time runs slightly slower than it does for someone in orbit. The difference is tiny but measurable, about 45 microseconds per day. This might seem negligible, but it's crucial for technologies requiring precise timing. Atomic clocks, accurate to within 1 second over millions of years, can detect these minute differences. In 1976, physicists conducted the Gravity Probe A experiment, launching an atomic clock 22 kilometers high on a rocket. The clock ran faster at higher altitude, exactly as Einstein's equations predicted, confirming gravitational time dilation with remarkable precision. The effect becomes dramatic near extremely massive objects. Consider a neutron star, where matter is compressed to incredible density. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. Near such an object, gravitational time dilation becomes severe. An observer watching someone approach a neutron star would see them moving in increasingly slow motion as they descended deeper into the gravitational field. Black holes represent the extreme case. At the event horizon, the boundary beyond which nothing can escape, time dilation becomes infinite from an outside observer's perspective. Someone falling toward a black hole would appear to slow down and freeze at the event horizon, their image growing dimmer and redder as light struggles to escape the intense gravity. Yet from the falling person's viewpoint, they would pass through the event horizon normally, experiencing no unusual time effects locally. This gravitational warping of time has practical consequences throughout the universe. Light climbing out of gravitational wells loses energy and becomes redshifted, its wavelength stretched toward the red end of the spectrum. Astronomers observe this gravitational redshift in light from white dwarf stars, whose intense gravity stretches the wavelengths of photons escaping their surfaces. The Global Positioning System provides a daily demonstration of gravitational time dilation's reality. GPS satellites orbit at about 20,000 kilometers altitude, where Earth's gravity is weaker than at the surface. Their clocks run approximately 45 microseconds per day faster than ground-based clocks due to this reduced gravitational time dilation. Combined with the special relativistic effect of their orbital motion, GPS satellites require constant time corrections to maintain accuracy. Mountain climbers experience gravitational time dilation too, though imperceptibly. At the summit of Mount Everest, nearly 9 kilometers above sea level, time passes about 30 nanoseconds per day faster than at sea level. Over a lifetime, a mountain dweller would age about 90 nanoseconds more than someone at sea level, a difference far too small to notice but perfectly real according to Einstein's equations. One of the most profound implications of Einstein's relativity is that simultaneity, the notion of events happening at the same time, is not absolute but depends entirely on the observer's motion. This relativity of simultaneity fundamentally challenges our intuitive understanding of time and reveals why there's no universal now spanning the cosmos. To understand this concept, imagine two lightning bolts striking the ends of a moving train simultaneously, as observed by someone standing on the platform. The platform observer sees both flashes at the same time because they're equidistant from both strikes. However, a passenger on the train, moving toward one lightning bolt and away from the other, will see the forward strike first and the rear strike later. From the train passenger's perspective, the lightning bolts did not strike simultaneously. This isn't merely about the time it takes light to travel. Even accounting for light travel time, the events genuinely occur at different times in the train passenger's reference frame. The relativity of simultaneity means that the temporal order of spatially separated events can differ for observers in relative motion, provided the events are not causally connected. Consider two distant stars exploding as supernovae. An astronomer on Earth might observe these explosions as simultaneous events. However, an alien observer traveling at high speed relative to Earth would measure these same explosions occurring at different times. Neither observer is wrong. Simultaneity simply doesn't exist as an absolute concept in our universe. The mathematical relationship governing this effect involves the Lorentz transformation, which describes how space and time coordinates change between reference frames. For two events separated by distance and occurring simultaneously in one frame, an observer moving at velocity v will measure a time difference equal to negative velocity times distance divided by the speed of light squared. This formula quantifies how motion destroys simultaneity. This relativity has profound implications for our understanding of causality. Events can only influence each other if they're connected by signals traveling at or below light speed. If two events are space-like separated, meaning the distance between them is greater than light could travel in the time between them, then no causal relationship exists. Different observers may disagree about which event occurred first, but this disagreement cannot lead to paradoxes because neither event can influence the other. The concept becomes even more striking when we consider cosmic scales. Imagine an alien civilization in the Andromeda Galaxy, 2.5 million light-years away. If they're moving relative to us at just a few kilometers per second, their notion of simultaneity with events on Earth could differ by thousands of years. What they consider now on Earth might correspond to events in our distant past or future. This relativity of simultaneity explains why faster-than-light communication would create paradoxes. If we could send instantaneous messages across space, different observers would disagree about the order in which messages were sent and received. Some observers might see replies arriving before questions were asked, violating causality and creating logical contradictions. The implications extend to our understanding of free will and determinism. If the future already exists in some reference frames now, what does this mean for our choices and actions? Physicists and philosophers continue debating these deep questions, but the mathematics of relativity clearly shows that simultaneity is observer-dependent, not a fundamental feature of reality. When we expand our perspective to cosmic scales, the relativity of simultaneity and time dilation create a universe where now becomes a meaningless concept beyond our local reference frame. The vast distances between celestial objects, combined with the finite speed of light, mean that our observations of the cosmos are always glimpses into the past, creating a complex temporal landscape across space. Light from the sun takes approximately 8 minutes and 20 seconds to reach Earth. When we observe the sun, we're seeing it as it existed 8 minutes ago, not as it is now. This light travel time effect becomes more dramatic with distance. The nearest star system, Alpha Centauri, appears to us as it was 4 years and 4 months ago. The Andromeda Galaxy shows itself as it existed 2.5 million years in the past. But the situation is far more complex than simple light travel delays. Due to the relativity of simultaneity, different observers throughout the universe would disagree about what constitutes the present moment on Earth. An observer moving toward our solar system at high speed would consider events in Earth's future to be happening now, while an observer moving away would consider events in Earth's past as simultaneous with their present. Consider the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all space. This radiation was emitted when the universe was only 380,000 years old, about 13.8 billion years ago. Every direction we look, we see this ancient light, creating a spherical surface in spacetime called the surface of last scattering. This represents the most distant now we can observe, but it's actually the most ancient past accessible to our instruments. Galaxy clusters, the largest gravitationally bound structures in the universe, demonstrate time dilation on cosmic scales. These massive collections of galaxies create significant gravitational fields that slow time relative to the nearly empty voids between them. An observer in a dense galaxy cluster would age slightly more slowly than someone in the cosmic voids, though the effect is small compared to what occurs near black holes or neutron stars. The expansion of the universe adds another layer of complexity to cosmic time. As space itself stretches, distant galaxies recede from us at velocities that increase with distance. The most distant observable galaxies move away at significant fractions of light speed due to cosmic expansion. This motion creates relativistic effects that influence how we observe their evolution and aging processes. Quasars, the brilliant cores of active galaxies powered by supermassive black holes, provide dramatic examples of cosmic time effects. These objects, often billions of light years away, show us the universe as it existed when it was much younger. The light we receive from the most distant quasars began its journey when the universe was less than 1 billion years old, offering windows into cosmic adolescence. The concept of cosmic time, used by cosmologists to describe the universe's age and evolution, represents time as measured by observers at rest relative to the cosmic microwave background. This provides a useful universal reference frame, but it's important to remember that this choice is conventional, not fundamental. The universe itself doesn't have a preferred reference frame or absolute time. Gravitational waves, ripples in spacetime itself, travel at light speed and carry information about cosmic events like black hole mergers and neutron star collisions. When we detect these waves, we're observing spacetime distortions that occurred millions or billions of years ago. The waves themselves experienced no time dilation during their journey, but the sources that created them existed in the distant past of our reference frame. The strange behavior of time across the universe isn't merely theoretical speculation. Modern technology and astronomical observations provide daily confirmation of these relativistic effects, demonstrating how time dilation and simultaneity's relativity shape our understanding of the cosmos and enable crucial technologies we depend upon. The Global Positioning System serves as perhaps the most practical demonstration of relativistic time effects. GPS satellites orbit Earth at approximately 20,000 kilometers altitude, traveling at speeds of about 14,000 kilometers per hour. These satellites experience both special and general relativistic effects that would render the system useless without proper corrections. Special relativity causes the satellite clocks to run slower by about 7 microseconds per day due to their high orbital velocity. Simultaneously, general relativity causes these same clocks to run faster by about 45 microseconds per day because they experience weaker gravity at their orbital altitude. The net effect is that satellite clocks gain about 38 microseconds daily compared to ground-based clocks. This might seem like a tiny discrepancy, but GPS requires nanosecond precision to determine positions accurately. Light travels about 30 centimeters in 1 nanosecond, so timing errors of microseconds would translate to positioning errors of hundreds of meters. Without relativistic corrections, GPS would become increasingly inaccurate, accumulating errors of several kilometers per day. Particle accelerators provide another arena where relativistic time effects are routine. The Large Hadron Collider accelerates protons to 99.999991% of light speed. At these velocities, time dilation factors reach 7,460. Particles that would normally decay in microseconds persist for milliseconds in the laboratory frame, allowing physicists to study their properties and interactions. Muons created by cosmic ray interactions in Earth's upper atmosphere demonstrate natural time dilation. These particles have a mean lifetime of only 2.2 microseconds, which should allow them to travel just 660 meters before decaying. However, muons created 20 kilometers high in the atmosphere regularly reach Earth's surface because time dilation extends their lifetimes in our reference frame. Astronomical observations reveal gravitational time dilation throughout the universe. White dwarf stars, with surface gravities hundreds of thousands of times stronger than Earth's, show gravitational redshift in their spectral lines. Light climbing out of these intense gravitational fields loses energy, its wavelength stretched toward the red end of the spectrum exactly as Einstein's equations predict. Neutron stars provide even more extreme examples. These incredibly dense objects, containing more mass than the Sun compressed into a sphere just 20 kilometers across, create gravitational fields so intense that time dilation becomes readily observable. Pulsars, rotating neutron stars that emit regular radio pulses, show timing variations that include gravitational time dilation effects. The binary pulsar discovered by Russell Hulse and Joseph Taylor provides exquisite confirmation of general relativity. This system consists of two neutron stars orbiting each other every 7 hours and 45 minutes. The orbital decay rate, caused by energy loss to gravitational waves, matches Einstein's predictions to within 0.2% accuracy. Very long baseline interferometry, a technique that combines radio telescope observations from around the globe, must account for relativistic effects to achieve its extraordinary precision. The technique can measure celestial positions to microarcsecond accuracy, but this requires careful consideration of time dilation effects at different observatory locations and the relativity of simultaneity across the baseline distances. Atomic clocks have become so precise that they can detect gravitational time dilation over height differences of just centimeters. In 2010, researchers at the National Institute of Standards and Technology demonstrated that atomic clocks separated by 33 centimeters in height could measure the resulting gravitational time dilation, opening new possibilities for precision tests of relativity and practical applications in geodesy and fundamental physics research. As we reach the culmination of our journey through time's relativistic nature, we must confront a profound truth: the universe has no universal now. This realization fundamentally transforms our understanding of existence, consciousness, and our place in the cosmic order, revealing that our everyday experience of time represents just one local perspective in an infinitely complex temporal landscape. The absence of absolute simultaneity means that events we consider simultaneous on Earth may be separated by vast time intervals when viewed from other reference frames throughout the universe. An alien observer in a distant galaxy, moving at high speed relative to our solar system, might consider events from Earth's Jurassic period to be happening now, while another observer might consider events from our far future as simultaneous with their present moment. This relativity extends to the very concept of existence itself. When we ask whether a distant star exists right now, we're asking a question that has no absolute answer. The star's current state depends entirely on our chosen reference frame and definition of simultaneity. In one frame, the star might have exploded millions of years ago. In another, it continues burning steadily. In yet another, it hasn't even formed yet. The block universe interpretation of relativity suggests that all events, past, present, and future, exist equally in a four-dimensional spacetime continuum. From this perspective, time doesn't flow but rather represents a dimension through which conscious observers move, creating the illusion of temporal passage. Your birth, your current moment listening to these words, and your eventual death all exist as equally real events in the spacetime block. This view challenges our intuitive understanding of free will and causality. If the future already exists in some sense, are our choices predetermined? Physicists and philosophers continue debating these questions, but the mathematics of relativity clearly indicates that temporal relationships are far more complex than our everyday experience suggests. Consider the cosmic microwave background, that ancient afterglow of the Big Bang visible in every direction we look. This radiation defines a natural reference frame for the universe, allowing cosmologists to speak meaningfully about cosmic time and the universe's age. However, this choice remains conventional rather than fundamental. The universe itself recognizes no preferred reference frame or absolute temporal standard. The expansion of space adds another layer to our temporal confusion. Distant galaxies recede from us not through motion in space, but because space itself stretches between us. This cosmic expansion means that our observable universe represents a sphere of causally connected events, beyond which lie regions that can never influence us or be influenced by us. These causally disconnected regions might as well exist in separate universes from our temporal perspective. Black holes create the most extreme temporal distortions in the known universe. At the event horizon, time dilation becomes infinite from an outside observer's perspective. Information falling into a black hole appears to freeze at the horizon, creating a permanent record of everything the black hole has consumed. Yet from the infalling observer's viewpoint, they pass through the horizon normally, experiencing no unusual time effects until tidal forces tear them apart near the singularity. The search for quantum gravity, a theory unifying general relativity with quantum mechanics, may revolutionize our understanding of time at the smallest scales. Some theories suggest that time itself might be quantized, existing in discrete units rather than flowing continuously. Others propose that time emerges from more fundamental quantum processes, making temporal flow and approximation valid only at macroscopic scales. Despite these mind-bending implications, we must remember that relativity doesn't invalidate our everyday experience of time. Within our local reference frame, causality operates normally, clocks tick steadily, and the future remains unknown until it becomes the present. The strange behaviors of time manifest only when we compare widely separated reference frames or encounter extreme gravitational fields and velocities. The universe's lack of absolute simultaneity ultimately reveals the profound interconnectedness of space and time. We cannot speak meaningfully about cosmic events without specifying our observational perspective. This observer dependence doesn't make physics subjective, but rather highlights the deep relationship between geometry and physical law that Einstein discovered over a century ago. And on that note, we've journeyed through one of the most profound discoveries in human history, the realization that time itself is not the steady, universal constant we once believed it to be. From the time dilation experienced by GPS satellites to the infinite temporal distortions at black hole event horizons, from the relativity of simultaneity that destroys any universal now to the gravitational warping of time itself, we've seen how Einstein's insights continue to reshape our understanding of reality. The next time you glance at a clock or contemplate what's happening right now somewhere else in the universe, remember that you're experiencing just one local perspective in an infinitely rich temporal tapestry. Time flows differently throughout the cosmos, and simultaneity exists only within our limited reference frame. In the grand cosmic perspective, every moment that has ever existed or ever will exist shares an equal claim to reality. To understand how neutron stars create their celestial music, we must first witness their dramatic birth. When a supermassive star with an initial mass greater than about 8 times that of the Sun begins to die, it forms a red supergiant before exploding as a supernova. This explosion is one of the most violent events in the universe, releasing more energy in seconds than our Sun will produce in its entire 10 billion year lifetime. But within this cosmic violence lies the creation of something extraordinary. When the star's core collapses during the supernova, gravity becomes so intense that it crushes protons and electrons together, forcing them to merge into neutrons. Imagine taking all the mass of our Sun and squeezing it into a sphere only 12 miles across. The enormous density of a neutron star means a teaspoon of neutron star material would weigh 10 million tons. To put this in perspective, a normal-sized matchbox containing neutron star material would have a weight of approximately 3 billion tons. This process creates matter so dense that it exists nowhere else in the observable universe. The material becomes what physicists call degenerate matter, where the normal rules of physics as we know them begin to break down. Picture trying to fit all the people on Earth into a single city block, and you begin to approach the level of compression occurring inside these stellar remnants. During this collapse, 2 crucial properties are preserved and intensified. First, the original star's rotation speeds up dramatically, much like a figure skater pulling in their arms during a spin. A star that once rotated every few weeks might become a neutron star spinning hundreds of times per second. The fastest spinning neutron star on record, found in a globular cluster of stars located around 28,000 light-years from Earth, spins around 716 times per second. Second, the star's magnetic field becomes concentrated into an area millions of times smaller, amplifying its strength to incomprehensible levels. Neutron stars have exceptionally strong magnetic fields around them, often billions or even trillions of times stronger than Earth's protective magnetic field. To visualize this, imagine Earth's gentle magnetic field, barely strong enough to move a compass needle, amplified until it could lift a car from miles away. These 2 properties, ultra-rapid rotation and incredibly powerful magnetic fields, work together to transform the neutron star into something remarkable, a cosmic beacon that sweeps beams of radiation across space with the precision of an atomic clock. The neutron star's magnetic field acts like a funnel, channeling charged particles from its surface into narrow beams that shoot out from its magnetic poles. As the neutron star spins, these beams sweep across space like the rotating beam of a lighthouse. When one of these beams happens to point toward Earth during its rotation, our radio telescopes detect a brief pulse of radio waves. This creates the rhythmic pattern that gives these objects their name, pulsars, short for pulsating stars, though they are not actually pulsating at all but simply rotating. The birth of each neutron star represents a cosmic recycling program of extraordinary proportions. The heavy elements forged in the original star's nuclear furnace are scattered across space by the supernova explosion, eventually becoming the building blocks for new stars, planets, and perhaps even life itself. Meanwhile, the collapsed core continues its eternal dance, spinning and pulsing, creating a cosmic metronome that can keep more accurate time than our most precise atomic clocks here on Earth. Understanding how neutron stars create their signature pulses requires examining their remarkable internal structure and the invisible architecture of their magnetic fields. These objects are far from simple. They are among the most complex and exotic structures in the universe, with physics that pushes the boundaries of our understanding. The combination of intense gravity, high temperature, and extreme density makes neutron stars like nothing we can produce on Earth. At their surface, gravity is so strong that if you could somehow stand there, you would weigh about 1 billion times more than you do on Earth. The surface itself is thought to be a crystalline lattice of atomic nuclei, creating what might be the strongest material in the universe, trillions of times harder than diamond. Beneath this surface lies a landscape that defies imagination. The outer crust contains nuclei arranged in a crystal lattice, immersed in a sea of electrons. As we journey deeper, the density increases so dramatically that normal atomic nuclei begin to merge and elongate into structures that physicists poetically call nuclear pasta, forming shapes that resemble lasagna sheets, spaghetti strands, and gnocchi balls, depending on the precise conditions. The core of a neutron star remains one of physics' greatest mysteries. Here, matter exists in forms that we cannot replicate or fully understand. Some theories suggest the presence of exotic particles that exist nowhere else in the universe, strange quarks, hyperons, or even more exotic forms of matter that challenge our understanding of the fundamental building blocks of reality. But it is the neutron star's magnetic field that creates the cosmic music we observe. Pulsars have very strong magnetic fields which funnel jets of particles out along the two magnetic poles. These accelerated particles produce very powerful beams of light. Often, the magnetic field is not aligned with the spin axis, so those beams of particles and light are swept around as the neutron star rotates. Picture a bar magnet spinning inside a globe filled with charged particles. The magnetic field lines stretch from one pole to the other, but they are not aligned with the rotation axis. Instead, they are tilted at an angle, creating a complex, twisted structure that rotates with the star. This misalignment is crucial because it creates the lighthouse effect that allows us to detect these objects from across the galaxy. The magnetic field acts as a cosmic particle accelerator. A gamma-ray pulsar is a compact neutron star that accelerates charged particles to relativistic speeds in its extremely strong magnetic field. Near the magnetic poles, particles are accelerated to nearly the speed of light, creating intense beams of radiation that extend far into space. These beams are not simply points of light, but rather complex cones of radiation that include radio waves, optical light, X-rays, and gamma rays. The radio waves that we detect on Earth are just one small part of this electromagnetic symphony. The beams are so narrow and intense that they can remain detectable across thousands of light years, like cosmic searchlights cutting through the darkness of space. The precision of these rotating beams is extraordinary. Some pulsars maintain timing accuracy that rivals or exceeds our best atomic clocks. This reliability comes from the neutron star's immense rotational inertia. Once spinning, these objects resist any change to their rotation with tremendous persistence. Their enormous density means that even tiny changes in their structure or magnetic field take enormous amounts of energy to accomplish. The magnetic field structure itself is dynamic and evolving. Over millions of years, the field gradually weakens as energy is radiated away, and the pulsar's rotation slowly decreases. This creates an evolutionary sequence where young, rapidly spinning pulsars with strong magnetic fields gradually age into slower, quieter objects that eventually fade from our ability to detect them. The cosmic music of neutron stars manifests most clearly in the radio waves that sweep across our galaxy, creating patterns of extraordinary beauty and precision. Pulsars are magnetized neutron stars that appear to emit periodic short pulses of radio radiation with periods between 1 and 4 milliseconds and 8 and 5 seconds. This range encompasses a remarkable variety of cosmic rhythms, from rapid-fire drumbeats to slow, stately pulses that mark time like a grandfather clock in the cosmos. The mechanism behind this radio emission remained a mystery for decades after the first pulsar was discovered in 1967. In 1967, shortly before the discovery of pulsars, Franco Pacini suggested that a rotating neutron star with a magnetic field would emit radiation, and even noted that such energy could be pumped into a supernova remnant around a neutron star, such as the Crab Nebula. Recent research has finally begun to unravel this cosmic mystery. The wobbling electric fields in the presence of the pulsar's powerful magnetic fields then result in electromagnetic waves that escape into space. Using plasma simulations, the researchers found that these electromagnetic waves match radio waves observed from pulsars. This breakthrough helps us understand how the immense magnetic fields and rapid rotation work together to generate the radio signals we detect. The process begins in the neutron star's magnetosphere, a region of space dominated by the star's magnetic field. This invisible structure extends thousands of miles into space, creating a complex playground for charged particles. As the neutron star rotates, it drags this magnetic field with it, creating electric fields that accelerate particles to incredible speeds. Near the magnetic poles, conditions become extreme. The rotating magnetic field creates gaps where particles can be accelerated to nearly the speed of light. As these relativistic particles spiral along magnetic field lines, they emit synchrotron radiation across the electromagnetic spectrum. The radio waves we detect are created through a complex cascade process, where high-energy particles create pairs of electrons and positrons, which in turn produce the radio emission through collective plasma effects. The resulting radio pulses carry detailed information about their journey through space. As radio waves travel from the pulsar to Earth, they encounter the thin plasma that fills interstellar space. This plasma causes different radio frequencies to travel at slightly different speeds, creating a phenomenon called dispersion. Lower frequency radio waves arrive at Earth slightly later than higher frequencies from the same pulse. By measuring this time delay, astronomers can calculate exactly how much plasma the radio waves encountered on their journey, providing a direct measurement of the density of interstellar space. This technique has revealed the structure of our galaxy's interstellar medium in exquisite detail, showing bubbles of hot gas blown by stellar winds and the aftermath of ancient supernovae. The radio signals also reveal the pulsar's motion through space. As the neutron star moves toward or away from us, the Doppler effect shifts the arrival time of pulses, allowing astronomers to measure velocities with incredible precision. Some pulsars are moving through space at hundreds of miles per second, kicked into motion by the asymmetric explosion that created them. Perhaps most remarkably, the timing of pulsar signals is so precise that they can be used as cosmic clocks. A millisecond pulsar is one with a rotational period between 1 and 10 milliseconds, or from 60,000 to 6,000 revolutions per minute. These rapidly spinning objects maintain their rhythm with such accuracy that they can be used to detect gravitational waves, minute ripples in spacetime itself that cause tiny changes in the arrival times of pulsar signals. The radio symphony of pulsars thus provides us with a window into some of the most fundamental aspects of physics and astronomy, from the structure of matter at nuclear densities to the nature of space and time itself. The magnetic fields of neutron stars orchestrate some of the universe's most spectacular phenomena, creating structures and processes that exist nowhere else in nature. These fields are not static entities but dynamic, evolving systems that shape the space around the neutron star and control the flow of matter and energy in ways that continue to astound astronomers and physicists. To appreciate the scale of these magnetic fields, consider that Earth's magnetic field, which protects us from harmful solar radiation and guides compass needles, measures about half a Gauss at our planet's surface. A typical neutron star's magnetic field ranges from 1 billion to 1 trillion Gauss, with some exotic objects called magnetars reaching fields of up to 1 quadrillion Gauss. At such intensities, the magnetic field contains enough energy to power our sun for millions of years. These fields create a complex three-dimensional structure around the neutron star called the magnetosphere. Unlike Earth's relatively simple dipole field, which resembles the pattern around a bar magnet, neutron star magnetospheres are twisted, dynamic regions where the normal rules of physics are pushed to their limits. The rapidly rotating magnetic field drags plasma along with it, creating currents that flow along invisible field lines like traffic on cosmic highways. The interaction between rotation and magnetic field creates distinct regions within the magnetosphere. Close to the neutron star, within the light cylinder, a theoretical boundary where the rotational velocity would equal the speed of light, the magnetic field forces plasma to rotate with the star. Beyond this boundary, field lines stretch and reconnect, creating open zones where particles can escape into space. At the magnetic poles, the field lines converge and create natural particle accelerators. Here, the combination of the strong magnetic field and the electric field generated by rotation creates gaps where particles gain enormous energies. Electrons and positrons are accelerated to speeds approaching that of light, creating cascades of secondary particles through interactions with intense gamma rays. The magnetic field also controls how matter falls onto the neutron star. In binary systems where a neutron star orbits a companion star, material from the companion can be captured by the neutron star's gravity. However, this material cannot fall directly onto the surface. Instead, the magnetic field funnels it toward the magnetic poles, creating hot spots where the infalling matter crashes into the neutron star's surface at tremendous speeds. This process creates some of the most energetic phenomena in the universe. As matter accelerates toward the neutron star, it heats up to temperatures of millions of degrees, emitting X-rays and gamma rays. The hot spots at the magnetic poles create beams of high-energy radiation that sweep across space as the neutron star rotates, much like the radio beams but at much higher energies. The magnetic field structure is not permanent but evolves over time through several mechanisms. All pulsars slow down gradually as they age. The radiation emitted by a pulsar is jointly powered by its magnetic field and its spin. As energy is carried away by electromagnetic radiation, both the rotation rate and magnetic field strength gradually decrease over millions of years. Some neutron stars experience sudden changes in their magnetic field configuration through events called magnetar flares. These are thought to occur when a neutron star's crust suddenly cracks under magnetic stress, allowing field lines to reconnect in a new configuration. The energy released in these events can be detected across the galaxy, briefly outshining all other X-ray sources in the sky. The magnetic field also plays a crucial role in the neutron star's long-term evolution. Young pulsars with strong magnetic fields eventually evolve into millisecond pulsars through a process of magnetic field decay and spin up by matter accretion from a companion star. This evolutionary pathway connects the rapid pulsars we observe to the slower, older objects that represent their eventual fate. The rhythmic pulses of neutron stars have transformed our understanding of time itself, creating cosmic chronometers that surpass even our most precise atomic clocks in their stability and accuracy. These celestial timepieces provide insights not only into the nature of neutron stars themselves, but also into fundamental physics and the structure of the universe around us. The discovery that pulsars could serve as extraordinarily precise clocks came as a surprise to early astronomers. The first pulsars were discovered through their extremely regular pulses of radio waves, but it took time to realize just how regular these signals could be. Some millisecond pulsars maintain timing accuracy that allows astronomers to predict the arrival of pulses years in advance with precision measured in microseconds. This extraordinary regularity stems from the neutron star's immense rotational inertia. The star's incredible density means that once it is spinning, enormous forces are required to change its rotation rate. Think of trying to slow down a massive flywheel versus stopping a spinning coin. The neutron star's rotation is so stable that even earthquakes on its surface, involving the sudden rearrangement of matter weighing as much as mountains on Earth, produce only tiny, measurable changes in the pulse timing. These timing variations tell fascinating stories about the neutron stars themselves. Occasionally, a pulsar will suddenly speed up slightly in an event called a glitch. These glitches are thought to occur when the neutron star's crust, which rotates slightly slower than its interior, suddenly cracks and readjusts to match the faster rotation of the core. The resulting change in pulse timing provides direct evidence of the neutron star's internal structure and the exotic physics occurring within. The precision of pulsar timing has opened up entirely new fields of astronomy. By carefully monitoring the arrival times of pulses over years or decades, astronomers can detect incredibly subtle effects. When a pulsar is part of a binary system orbiting around another star, the gravitational field of the companion causes small but measurable changes in the pulse arrival times as the pulsar moves toward and away from Earth in its orbit. These orbital measurements have provided some of the most stringent tests of Einstein's theory of general relativity. The first indirect evidence for gravitational waves came from observations of a binary pulsar system, where the two stars are spiraling inward as they lose energy to gravitational radiation. The rate of orbital decay matched Einstein's predictions with remarkable precision, earning the discoverers a Nobel Prize and confirming one of the theory's most subtle predictions. Pulsar timing arrays, networks of telescopes monitoring dozens of millisecond pulsars simultaneously, have become instruments for detecting gravitational waves directly. When gravitational waves from distant sources pass through our region of space, they cause tiny changes in the distances between Earth and the pulsars, showing up as correlated timing variations across multiple pulsars. This technique is sensitive to gravitational waves with much longer wavelengths than can be detected by ground-based instruments. The variety of pulsar rhythms spans an enormous range. Young pulsars typically rotate every few seconds, their powerful magnetic fields gradually slowing their rotation as energy is radiated away. Middle-aged pulsars may pulse once per second, while the fastest millisecond pulsars complete hundreds of rotations in a single second. Each category provides different insights into neutron star physics and evolution. Some pulsars exhibit complex timing behavior that reveals additional layers of physics. Intermittent pulsars switch on and off unpredictably, while others show gradual changes in pulse shape and intensity. These variations reflect changes in the magnetospheric processes that create the radio emission, providing laboratories for studying plasma physics under conditions impossible to recreate on Earth. The study of pulsar timing continues to yield surprises and discoveries. Recent observations have revealed pulsars with timing noise, random fluctuations that may result from turbulence in the neutron star's magnetosphere or changes in its internal structure. As we reach the end of our journey through the realm of neutron star music, we find ourselves contemplating objects that represent some of the most extreme physics in the universe while simultaneously providing us with tools to explore the cosmos with unprecedented precision. These gentle giants, despite their violent births and incredible densities, offer us a peaceful, rhythmic connection to the fundamental processes that govern reality itself. The radio telescopes that capture pulsar signals are among humanity's most sensitive listening devices. They can detect signals so faint that the total energy collected from all pulsars ever observed would not be enough to lift a feather. Yet within these whisper-quiet signals lies information about physics at the edge of our understanding. Each pulse carries data about the neutron star's magnetic field, its rotation, its motion through space, and even the structure of the interstellar medium through which the radio waves have traveled. Modern pulsar astronomy continues to reveal new wonders. Recent observations have found at least 2 neutron stars with a mass about twice the mass of the Sun, perhaps even more. These massive neutron stars challenge our understanding of how matter behaves at nuclear densities and provide crucial constraints on the equation of state of ultra-dense matter. The discovery of neutron star mergers through gravitational wave detections has opened another chapter in understanding these objects. The gravitational waves produced in a merger of 2 neutron stars provide rich information on the structure of these exotic objects, in which a mass roughly comparable to that of the Sun is squeezed into a sphere with a radius of about 6 miles. These cataclysmic events create conditions even more extreme than those inside individual neutron stars, forging heavy elements and providing laboratories for studying matter under the most intense conditions possible. The relationship between neutron stars and their environment continues to surprise astronomers. The magnetic fields channel matter surrounding the neutron star into light-emitting jets, much like those we see near some black holes. This similarity between neutron star and black hole phenomena suggests deep connections in how compact objects interact with their surroundings, despite their very different natures. Looking toward the future, next-generation radio telescopes promise to detect thousands of new pulsars, creating a galactic network of cosmic chronometers. These surveys will map the structure of our galaxy in 3 dimensions, trace the history of stellar formation and death, and perhaps detect exotic objects like pulsar black hole binary systems that could provide even more stringent tests of fundamental physics. The search for extraterrestrial intelligence has also adopted pulsar timing as a potential communication medium. The incredible precision and stability of millisecond pulsars could, in principle, be used to encode information in timing variations detectable across interstellar distances. Whether nature or intelligence might employ such methods remains an open question, but it illustrates the profound impact these objects have had on our thinking about communication and information in the cosmos. As space-based telescopes become more sophisticated, we are beginning to observe pulsars across the entire electromagnetic spectrum simultaneously. This comprehensive view reveals the full complexity of neutron star magnetospheres and the processes that create their multi-wavelength emissions. Future missions may even detect individual neutron star oscillations, opening up neutron star seismology as a new field of study. The gentle giants we have explored tonight represent more than scientific curiosities. They are natural laboratories where the laws of physics are tested under conditions we can never hope to recreate artificially. They are cosmic lighthouses guiding our understanding of spacetime, gravity, and the fundamental nature of matter itself. And they are timekeepers, marking the passage of cosmic ages with precision that humbles our greatest technological achievements. you look up at the night sky, you're not seeing the universe as it is right now. You're witnessing a cosmic museum where every point of light represents a different moment in the universe's past. This is because light, despite traveling at the fastest speed possible in our universe, still takes time to journey across the vast distances between stars and galaxies. Think of light like a message in a bottle, cast into the cosmic ocean billions of years ago. When we catch these bottled messages with our telescopes, we're reading letters from the universe's distant past. The nearest star to our sun, Proxima Centauri, sends us light that's already 4 years old by the time it reaches our eyes. But this is nothing compared to the ancient messages we receive from distant galaxies. The speed of light is approximately 300,000 kilometers per second. While this seems incredibly fast, the universe is so enormously vast that even light takes billions of years to travel from the most distant observable objects to our telescopes. A light year, the distance light travels in 1 year, equals about 9.5 trillion kilometers. When astronomers say a galaxy is 10 billion light years away, they mean we're seeing that galaxy as it appeared 10 billion years ago. This cosmic time delay creates what astronomers call a light travel time effect. It transforms our telescopes into time machines, allowing us to observe the universe at different epochs simply by looking at objects at different distances. The farther away an object is, the further back in time we're seeing it. This principle forms the foundation of cosmic archaeology, where light becomes our primary tool for excavating the universe's history. The most distant galaxies we can observe appear as they were when the universe was less than 1 billion years old, compared to its current age of about 13.8 billion years. These ancient galaxies show us a cosmos that was dramatically different from today, filled with active star formation and cosmic violence that shaped the large-scale structure we observe in the modern universe. Modern telescopes function as sophisticated time machines, each one designed to capture and analyze the ancient photons that have traveled across cosmic distances. The Hubble Space Telescope, launched in 1990, revolutionized our ability to peer deep into cosmic history. Its position above Earth's atmosphere allows it to collect pristine images of galaxies as they appeared billions of years ago. When astronomers point Hubble toward a seemingly empty patch of sky and collect light for days or weeks, something magical happens. What initially appears as cosmic darkness gradually reveals itself to be filled with thousands of galaxies, each one an island universe containing hundreds of billions of stars. These deep field observations, like the famous Hubble Deep Field taken in 1995, show us galaxies so distant that their light has been traveling toward us for most of the universe's lifetime. The James Webb Space Telescope, which began operations in 2022, has pushed our cosmic vision even further into the past. Its massive mirror and infrared sensitivity allow it to detect the faintest whispers of light from the universe's first galaxies. Webb can observe galaxies that formed when the universe was only a few 100 million years old, during what astronomers call the cosmic dawn. Ground-based telescopes also contribute to this cosmic archaeology. Observatories like the Atacama Large Millimeter Array in Chile can detect radiation from dust and gas in distant galaxies, revealing the raw materials that fuel star formation across cosmic time. The Keck Observatory in Hawaii uses adaptive optics to peer through Earth's turbulent atmosphere, creating images so sharp they rival those from space. Each telescope observes different wavelengths of light, providing unique insights into cosmic history. Optical telescopes reveal the starlight from ancient galaxies, while radio telescopes detect the signatures of hydrogen gas that fuels cosmic evolution. Infrared telescopes can peer through cosmic dust clouds, revealing hidden star formation in the universe's past. Together, These instruments create a comprehensive picture of how the universe has evolved from its earliest epochs to the present day. Every galaxy carries within its starlight a detailed biography of its formation and evolution. Astronomers have developed sophisticated techniques to decode these stellar stories, reading the cosmic equivalent of tree rings and the light spectra of distant galaxies. This process, called stellar archaeology, reveals not just when stars formed, but under what conditions and from what materials. The color of a galaxy tells us about the ages of its stars. Blue galaxies are typically filled with young, hot stars that burn brightly but briefly, indicating ongoing star formation. Red galaxies, by contrast, are dominated by older, cooler stars, suggesting that their most vigorous star-forming days are behind them. By studying how the colors of galaxies change with cosmic time, astronomers can trace the universe's star formation history. Spectroscopy allows astronomers to dissect galactic light into its component wavelengths, revealing the chemical fingerprints of stars and gas within distant galaxies. Each element absorbs and emits light at specific wavelengths, creating a unique signature that astronomers can identify even across billions of light years. These spectral lines tell us about the metals forged in ancient stars and scattered into space by stellar explosions. The chemical composition of distant galaxies reveals the gradual enrichment of the universe with heavy elements. The first stars in the universe were made almost entirely of hydrogen and helium, the primordial elements created in the Big Bang. As these stars existed and died, they forged heavier elements in their cores and scattered them into space through stellar currents and supernova explosions. Each successive generation of stars inherited this chemical legacy, gradually building up the periodic table of elements we see today. By comparing the chemical compositions of galaxies at different cosmic times, astronomers can trace this process of cosmic chemical evolution. Distant galaxies show us a universe with much lower concentrations of heavy elements, while nearby galaxies reveal the cumulative result of billions of years of stellar nucleosynthesis. This chemical archaeology helps us understand not just how galaxies evolved, but how the universe itself became capable of forming the complex chemistry necessary for planets and life. The universe's large-scale structure resembles a vast cosmic web, with galaxies strung along filaments of dark matter like dewdrops on spider silk. This cosmic architecture emerged from tiny density fluctuations in the early universe, which grew over billions of years through gravitational attraction. By studying how galaxies are distributed across cosmic time, astronomers can trace the growth of this cosmic web and understand how it shaped galactic evolution. Dark matter, an invisible substance that outweighs ordinary matter by more than 5 to 1, provides the gravitational scaffolding for galaxy formation. Although we cannot see dark matter directly, we can observe its effects on the distribution and motion of galaxies. Computer simulations that include dark matter successfully reproduce the observed large-scale structure of the universe, confirming its crucial role in cosmic architecture. In the early universe, small fluctuations in dark matter density began to collapse under their own gravity, forming what astronomers call dark matter halos. Ordinary matter fell into these gravitational wells, where it cooled and condensed to form the first stars and galaxies. This process of hierarchical structure formation means that smaller objects formed first, then merged and grew into larger structures over cosmic time. The cosmic web continues to influence galaxy evolution today. Galaxies located in dense galaxy clusters experience environmental effects that can shut down star formation, while galaxies in the sparse cosmic voids continue forming stars at a steady rate. By studying how galaxy properties depend on their environment at different cosmic epochs, astronomers can understand how the cosmic web shapes galactic evolution. Gravitational lensing provides another window into cosmic structure formation. When light from a distant galaxy passes near a massive foreground object, the gravity of that object bends the light rays, creating distorted or multiple images of the background galaxy. This cosmic magnifying glass effect allows astronomers to study galaxies that would otherwise be too faint to observe, extending our view even deeper into cosmic history. Strong gravitational lenses can magnify background galaxies by factors of 10 or more, revealing details about star formation and structure in the very early universe. At the hearts of most galaxies lurk supermassive black holes, cosmic giants containing millions or billions of times the mass of our Sun. These enigmatic objects play a crucial role in galactic evolution, regulating star formation and shaping the properties of their host galaxies across cosmic time. The discovery of supermassive black holes in distant galaxies has revealed their importance in the cosmic story. When material falls into a supermassive black hole, it forms an accretion disk that heats up and glows brilliantly, creating some of the most luminous objects in the universe. These active galactic nuclei, or quasars, can outshine their entire host galaxies, making them visible across enormous cosmic distances. The light from quasars provides a beacon that allows astronomers to study galaxy formation in the very early universe. The most distant quasars, observed when the universe was less than 1 billion years old, pose a puzzle for astronomers. How did supermassive black holes grow so large so quickly in the young universe? This question drives ongoing research into the formation of the first black holes, which may have formed directly from the collapse of massive gas clouds in the early universe, bypassing the normal stellar evolution process. Supermassive black holes and their host galaxies appear to evolve together in a cosmic dance. Observations reveal tight correlations between black hole masses and properties of their host galaxy bulges, suggesting that black hole growth and galaxy formation are intimately connected. This relationship appears to hold across cosmic time, indicating that the coevolution of black holes and galaxies has been ongoing since the early universe. The energy output from active supermassive black holes can have profound effects on their host galaxies. Powerful jets and currents driven by black hole accretion can heat and expel gas from galaxies, shutting down star formation in a process astronomers call feedback. This mechanism may explain why the most massive galaxies in the universe are typically red and dead, having exhausted their star-forming fuel through black hole-driven currents. By studying how this feedback process has operated across cosmic history, astronomers gain insights into one of the key mechanisms that shapes galactic evolution. The period known as Cosmic Dawn represents one of the most fascinating chapters in the universe's history, when the first stars ignited and began to illuminate the cosmic dark age. This epoch, occurring roughly 100 to 500 million years after the Big Bang, marks the transition from a universe filled only with dark matter and neutral hydrogen gas to one beginning to sparkle with the light of newborn stars. Before the first stars formed, the universe existed in what astronomers call the Dark Age. During this time, the cosmos had cooled enough for electrons and protons to combine into neutral hydrogen atoms, making the universe transparent to light for the first time since the Big Bang. However, there were no stars yet to produce that light, leaving the universe in a state of cosmic twilight, illuminated only by the fading afterglow of the Big Bang itself. The first stars, known as population 3 stars, were unlike any stars we see today. These primordial giants formed from gas clouds composed almost entirely of hydrogen and helium, lacking the heavier elements that help modern stars regulate their formation. Without these cooling agents, the first stars grew to enormous sizes, perhaps 100 to 300 times more massive than our Sun. These stellar behemoths burned brilliantly but briefly, existing only a few million years before exploding as spectacular supernovae. When these first stars ignited, they began the process of cosmic reionization, gradually transforming the neutral hydrogen gas that filled the universe back into ionized plasma. Picture the universe as a cosmic fog slowly being burned away by the light of the first stars. This process took hundreds of millions of years to complete, creating bubbles of ionized gas around early star-forming regions that gradually merged until the entire universe became transparent to ultraviolet light. The James Webb Space Telescope has provided our clearest glimpses yet of this cosmic dawn period. Webb's infrared vision can penetrate the dust that often obscures early star formation, revealing galaxies that formed when the universe was only 3 to 4% of its current age. These observations have revealed that galaxies formed and grew more rapidly in the early universe than many theoretical models predicted, suggesting that the processes of star formation and galaxy assembly were more efficient in the cosmic past than astronomers initially thought. The chemical signatures left by the first stars continue to influence cosmic evolution today. Every element heavier than lithium in the periodic table was forged in the nuclear furnaces of stars or created in stellar explosions. The first supernovae scattered these newly created elements into space, enriching the gas clouds that would form the next generation of stars. This process of cosmic chemical evolution continues today, with each stellar generation building upon the elemental legacy of its predecessors. The field of cosmic archaeology stands at the threshold of revolutionary discoveries, as new telescopes and techniques promise to push our cosmic vision even deeper into the universe's past. The James Webb Space Telescope has already begun to transform our understanding of early galaxy formation, revealing mature galaxies at cosmic times when the universe was supposed to be filled only with small, irregular star-forming systems. Future ground-based telescopes will dwarf current observatories in their light-gathering power. The extremely large telescope, currently under construction in Chile, will have a mere 39 meters across, providing unprecedented resolution and sensitivity for studying distant galaxies. This cosmic giant will be able to directly observe the first stars that formed in the universe, ending the cosmic dark age and beginning the process of cosmic reionization. Space-based missions planned for the coming decades will open new windows into cosmic history. The Nancy Grace Roman Space Telescope will survey enormous volumes of space, mapping the cosmic web and measuring how dark energy has affected cosmic expansion over time. The proposed Large Ultraviolet Optical Infrared Surveyor mission would provide even greater sensitivity than Webb, potentially capable of studying the atmospheres of Earth like planets around nearby stars. Gravitational wave astronomy represents a completely new approach to cosmic archaeology. As advanced laser interferometer gravitational wave observatory and similar detectors become more sensitive, they will detect mergers of black holes and neutron stars throughout cosmic history, providing insights into stellar evolution and compact object formation that complement traditional electromagnetic observations. The planned space-based laser interferometer space antenna mission will detect gravitational waves from supermassive black hole mergers, revealing how these cosmic giants grew and merged across cosmic time. Multi-messenger astronomy, which combines observations of light, gravitational waves, and cosmic rays from the same sources, promises to provide a more complete picture of cosmic evolution. Future surveys will automatically identify transient events across the entire sky, enabling rapid follow-up observations that can capture the fleeting signatures of cosmic catastrophes. Machine understanding algorithms will sift through this flood of data, identifying patterns and anomalies that human astronomers might miss. And on that note, we complete our gentle journey through cosmic archaeology, where ancient light serves as our guide to understanding the universe's vast history. We've explored how telescopes become time machines, how galaxies carry the stories of their formation written in starlight, and how the cosmic web provides the stage upon which the cosmic drama unfolds. From the chemical evolution traced in stellar spectra to the coevolution of supermassive black holes and their host galaxies, we've seen how astronomers have become cosmic detectives, piecing together the universe's biography from the faintest whispers of ancient light. The future promises even more remarkable discoveries as new telescopes and techniques push our cosmic vision ever deeper into the universe's past. As we stand at this moment in cosmic history, we find ourselves uniquely positioned to witness the universe's story unfolding before our eyes. Each night, ancient photons that began their journey when the cosmos was young finally reach our world, carrying with them the secrets of stellar nurseries, galactic collisions, and the birth of the very elements that make up our bodies. We are quite literally made of stardust, forged in the nuclear furnaces of ancient suns and scattered across the cosmos by stellar explosions that occurred billions of years before our solar system even existed. The profound beauty of cosmic archaeology lies not just in its scientific discoveries, but in how it connects us to the greater cosmic story. When we observe a galaxy 10 billion light-years away, we're not just seeing distant stars, we're witnessing our own cosmic ancestry. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all were created in the hearts of stars that died long before our sun was born. This cosmic perspective reminds us that we are not observers standing outside the universe looking in, but rather participants in an ongoing cosmic evolution that spans nearly 14 billion years. Perhaps most remarkably, through cosmic archaeology we've discovered that the universe itself is still writing its story. Star formation continues in distant galaxies, black holes still merge and grow, and the cosmic web continues to evolve under the influence of dark energy. We exist during a brief but magnificent chapter in this cosmic tale, blessed with the intelligence and curiosity to read the universe's memory written in starlight. In studying the cosmos, we ultimately study ourselves, for we are the universe becoming aware of its own existence, capable of looking back through time and marveling at the incredible journey that brought us to this moment of cosmic consciousness. The story of the Great Attractor begins in the 1970s, when astronomers were meticulously mapping the cosmic microwave background, the ancient light that fills our universe. Think of this background radiation as a gentle glow left over from the universe's infancy, like the warm embers of a cosmic fire that burned 14 billion years ago. As scientists studied this ancient light, they noticed something peculiar. The temperature of this background radiation wasn't perfectly uniform. In one particular direction in space, it was slightly warmer, by less than 1/100th of a degree. This tiny temperature difference might seem insignificant, but it revealed something profound about our cosmic motion. When we move toward a source of light, that light appears slightly bluer and warmer due to a phenomenon called the Doppler effect. It's the same principle that makes an approaching ambulance siren sound higher in pitch. The warmer cosmic microwave background in one direction meant our entire local group of galaxies, including the Milky Way, was racing towards something at an extraordinary speed. The discovery presented a puzzle that would take decades to fully understand. Here was clear evidence of an enormous gravitational influence, yet when astronomers pointed their telescopes in that direction, they couldn't see what was causing it. The mystery deepened when they realized the scale of what they were dealing with. This wasn't just our galaxy being pulled along, but thousands of galaxies spanning incredible distances, all moving in a coordinated flow toward this enigmatic destination. By the 1980s, scientists had confirmed that our entire local group of galaxies was racing through space at extraordinary velocities toward an unseen gravitational source. This invisible force became known as the Great Attractor, named for its ability to gravitationally attract vast collections of galaxies across hundreds of millions of light-years of space. The reason the Great Attractor remained invisible for so long lies in an unfortunate cosmic coincidence of perspective. Picture yourself trying to see through a thick forest. Even if something massive exists on the other side, the trees block your view completely. This is precisely what happens when we try to observe the Great Attractor from Earth. It lies directly behind what astronomers call the zone of avoidance, a region where our own Milky Way's disk, thick with dust and stars, obscures our view of the distant universe. The Great Attractor is obscured by the Milky Way's galactic plane, lying behind the zone of avoidance, so that in visible light wavelengths, the Great Attractor is difficult to observe directly. Imagine trying to steady a distant mountain while standing in the middle of a dense fog. The dust and gas in our galaxy's disk absorb and scatter light from objects beyond, making direct optical observation nearly impossible. However, astronomers are resourceful. They began using different wavelengths of light that could penetrate the cosmic dust. Radio waves and infrared light became their tools of choice, able to pierce through the veil that visible light could not. Through these observations, they began to piece together the structure of what lay hidden. They discovered not just one massive object, but a complex region filled with galaxy clusters and vast amounts of dark matter. The observed attraction suggests a localized concentration of mass having the order of 10 to the 16th power solar masses. To put this in perspective, imagine the mass of 10 million billion suns concentrated in a relatively small region of space. This enormous concentration of matter creates a gravitational well so deep that it influences the motion of galaxies hundreds of millions of light-years away. The gravitational pull from this region is so strong that it overcomes the natural expansion of the universe in our local cosmic neighborhood. The challenge of studying something you cannot directly see required astronomers to become cosmic detectives, using indirect evidence to map the invisible. They studied the motions of galaxies they could observe, tracking their velocities and directions to map the underlying gravitational field. Like following breadcrumbs through a dark forest, each galaxy's motion provided clues about the massive structure pulling them along their cosmic journey. Understanding how galaxies move through space requires us to think beyond the familiar motions we experience on Earth. In our cosmic neighborhood, galaxies aren't simply floating randomly through space. They flow like rivers, following invisible currents created by gravity. These cosmic streams carry galaxies along predictable paths toward regions of higher mass density, much like how water flows downhill toward valleys. In 1986, a group of astronomers observing the motions of the Milky Way and neighboring galaxies noted that the galaxies were moving toward the Hydra and Centaurus superclusters. This discovery marked a crucial step in understanding our cosmic motion. Astronomers found that our galaxy and its neighbors weren't just drifting aimlessly through space, but were part of a vast, organized flow of thousands of galaxies all heading in the same general direction. Picture a massive river system viewed from space, with countless tributaries flowing into larger streams, which eventually converge into a mighty river flowing toward the sea. This is essentially what happens with galaxies on cosmic scales. Small groups of galaxies merge into larger flows, which join even more massive streams, all eventually flowing toward regions of concentrated mass like the Great Attractor. The velocities involved are staggering. Our local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, moves through space at approximately 600 kilometers per second relative to the cosmic microwave background. To put this in perspective, at this speed, you could travel from Earth to the Moon in just 11 minutes. Yet despite these incredible velocities, the distances involved are so vast that this cosmic journey unfolds over hundreds of millions of years. Astronomers discovered that this motion isn't unique to our local region. Similar flows exist throughout the observable universe, with galaxies streaming toward various massive attractors. However, the Great Attractor stands out because of its proximity to us and its enormous influence on our cosmic neighborhood. By mapping these galactic flows, scientists began to understand the large-scale structure of the universe, revealing a cosmic web of matter connected by gravitational threads spanning billions of light years. As observational techniques improved, astronomers gradually began to peer through the cosmic dust and identify the actual structures responsible for the Great Attractor phenomenon. The breakthrough came when they focused on a region in the constellation Norma, where infrared and radio observations revealed something remarkable. Hidden behind the galactic dust was one of the most massive galaxy clusters in our cosmic vicinity. The Norma cluster is the closest massive galaxy cluster to the Milky Way and lies about 220 million light-years away. The enormous mass concentrated here and the consequent gravitational attraction mean that this region of space is known to astronomers as the Great Attractor. Imagine discovering a hidden metropolis behind a mountain range. The Norma cluster represents just such a cosmic city, packed with hundreds of large galaxies and surrounded by vast halos of dark matter. Galaxy clusters are among the largest gravitationally bound structures in the universe. They contain hundreds or even thousands of individual galaxies, all held together by gravity and embedded in enormous reservoirs of dark matter. The space between galaxies in these clusters fills with hot gas, heated to millions of degrees by the intense gravitational environment. This gas glows brightly in high-energy wavelengths, providing another way for astronomers to study these massive structures despite the optical obscuration. The Norma cluster, however, represents just one component of the Great Attractor region. As observations became more sophisticated, astronomers realized that this area contains multiple galaxy clusters, groups, and vast filaments of dark matter, all contributing to the total gravitational influence. It's like discovering that what you thought was a single mountain is actually part of an entire mountain range, each peak contributing to the overall topography of the region. The gravitational field created by this concentration of matter extends far beyond the visible clusters themselves. Dark matter, which makes up approximately 85% of all matter in the universe, forms invisible scaffolding that amplifies the gravitational effects. This dark matter doesn't interact with light, making it invisible to our telescopes, but its gravitational influence shapes the large-scale structure of the universe and guides the motion of galaxies across vast distances. The story of the Great Attractor took a remarkable turn in 2014 when astronomers made a discovery that revolutionized our understanding of our place in the universe. Using sophisticated mapping techniques that trace the flow of galaxies across hundreds of millions of light years, they discovered that our Milky Way galaxy belongs to an enormous structure called the Laniakea supercluster. The Laniakea supercluster encompasses approximately 100,000 galaxies stretched out over 520 million light years. To comprehend this scale, imagine trying to visualize a structure so vast that light itself takes over 500 million years to cross it. Within this cosmic metropolis, it has the approximate mass of 10 to the 17th power solar masses, or 100,000 times that of our galaxy. The name comes from Hawaiian, meaning immense heaven, a fitting description for this cosmic structure that serves as our galactic neighborhood. This study also clarifies the role of the Great Attractor, a gravitational focal point in intergalactic space that influences the motion of galaxies within the supercluster. Rather than being a mysterious external force pulling us toward an unknown destination, the Great Attractor represents the gravitational center of our own cosmic home. Think of the supercluster as a vast cosmic watershed. Just as rivers flow toward the ocean following the topography of the land, galaxies within the supercluster flow along gravitational currents toward its center of mass. The Great Attractor region represents the lowest point in this gravitational landscape, the cosmic equivalent of a valley where all the streams converge. This discovery fundamentally changed our cosmic perspective. Instead of being pulled towards some distant, alien structure, we're actually part of a vast gravitational family. The galaxies around us, including our Milky Way, are all siblings in this enormous cosmic structure, connected by invisible threads of gravity that have guided our dance through space for billions of years. Our motion toward the Great Attractor isn't a journey to a foreign destination, but rather a homecoming to the heart of our own cosmic neighborhood. The cosmic journey toward the Great Attractor unfolds on timescales that dwarf human imagination. To understand this motion, we must think in terms of cosmic time, where millions of years pass like moments and the stately dance of galaxies plays out over billions of years. Our local group's motion toward the Great Attractor began shortly after the formation of large-scale structure in the universe, when gravity started pulling matter together into the cosmic web we observe today. At our current velocity of over 1 million miles per hour, you might expect this cosmic journey to end relatively quickly. However, the distances involved are so staggering that this apparent speed becomes almost imperceptible on cosmic scales. The Great Attractor lies approximately 250 million light-years away, meaning that at our current rate of approach, we wouldn't reach it for many billions of years. To put this in perspective, this journey will take longer than the entire history of life on Earth. But the universe doesn't remain static during this long voyage. The expansion of space itself works against gravitational attraction, stretching the fabric of spacetime and increasing distances between distant objects. This cosmic expansion, driven by dark energy, acts like a cosmic headwind that slows our approach to the Great Attractor. In regions where gravity is strong enough, like within galaxy clusters and superclusters, this expansion can be overcome, allowing structures to grow and merge. As we journey through space, we're also part of other cosmic motions. Our solar system orbits the center of the Milky Way every 230 million years, while the Milky Way itself rotates and slowly approaches the Andromeda Galaxy. These multiple motions combine to create a complex trajectory through space, like a cosmic ballet where multiple dancers move in intricate patterns simultaneously. The ultimate fate of this journey depends on the balance between gravitational attraction and cosmic expansion. Current models suggest that while we'll continue moving toward the Great Attractor for billions of years, the accelerating expansion of the universe will eventually halt and reverse this motion. In the distant future, the components of the supercluster may begin to drift apart as cosmic expansion overwhelms even the strongest gravitational bonds, leaving each galaxy to face an increasingly lonely universe. The Great Attractor phenomenon has become one of our most important windows into understanding dark matter, the mysterious substance that makes up approximately 85% of all matter in the universe. While we cannot see dark matter directly, its gravitational effects are written across the cosmic landscape in the form of galactic motions and large-scale structure. The Great Attractor region serves as a natural laboratory for studying how this invisible matter shapes the evolution of the universe. Think of dark matter as the invisible scaffolding of the cosmos. Just as a building's framework determines its shape and stability even though we cannot see it through the walls, Dark matter provides the gravitational skeleton that holds together massive structures like galaxy clusters and superclusters. In the Great Attractor region, computer simulations suggest that vast halos of dark matter, each containing trillions of times the mass of our Sun, create the gravitational wells that trap and concentrate normal matter into the galaxies we observe. The distribution of dark matter in the Great Attractor region follows a complex three-dimensional web of filaments and nodes. These cosmic highways of dark matter stretch across hundreds of millions of light years, connecting galaxy clusters and guiding the flow of normal matter along their gravitational currents. Where these filaments intersect, we find the most massive galaxy clusters, like beads on an invisible cosmic string. Recent studies using gravitational lensing have begun to map this dark matter distribution directly. When light from distant galaxies passes through regions of concentrated dark matter, the gravitational field bends and distorts the light, creating subtle changes in the appearance of background galaxies. By carefully analyzing these distortions, astronomers can create maps of dark matter density, revealing the hidden architecture that drives the Great Attractor phenomenon. The Great Attractor also helps us understand how dark matter and normal matter interact during the formation of cosmic structure. While dark matter can only interact through gravity, normal matter can radiate energy and cool, allowing it to collapse more efficiently into dense structures. This difference means that dark matter forms the large-scale framework first, and normal matter subsequently flows along these gravitational channels to form the galaxies and clusters we observe. Understanding the dark matter connection has implications far beyond the Great Attractor itself. The same physical processes that created this massive structure operate throughout the universe, shaping the cosmic web on the largest scales. By studying how dark matter concentrates in regions like the Great Attractor, astronomers gain insights into the fundamental nature of this mysterious substance and its role in cosmic evolution. The discovery and study of the Great Attractor has profound implications for our understanding of the universe's structure and evolution. This cosmic phenomenon reveals that the universe is far more organized and interconnected than early astronomers could have imagined. Rather than galaxies moving randomly through space, we see evidence of vast, coherent flows that trace the underlying gravitational architecture of the cosmos. The Great Attractor, rather than anything to be afraid of, is where our local galaxies are heading to hang out, the central gravitational point of our local area of the universe. This perspective transforms our understanding of cosmic motion from something alien and threatening to something familiar and comforting. We're not being pulled toward an unknown fate, but rather flowing along the natural currents of our cosmic neighborhood. The study of the Great Attractor has also advanced our understanding of dark matter and its role in shaping cosmic structure. The gravitational effects we observe require far more mass than we can account for with visible matter alone. This invisible dark matter provides the gravitational scaffolding that holds together massive structures like Archaeology and creates the flows that guide galactic motion. Understanding these dark matter distributions helps astronomers map the invisible architecture of the universe. Furthermore, the Great Attractor phenomenon demonstrates how local gravitational effects can overcome cosmic expansion on certain scales. While the universe as a whole continues to expand, regions of sufficient mass density can resist this expansion and even contract under their own gravity. This balance between expansion and contraction shapes the evolution of cosmic structure and determines the fate of different regions of the universe. From a philosophical perspective, the Great Attractor reminds us of our deep connection to the cosmos. We often think of Earth, our solar system, or even our galaxy as isolated islands in space. However, the reality is that we're part of vast cosmic currents that connect us to structures spanning hundreds of millions of light years. Our motion through space isn't random or purposeless, but follows ancient gravitational pathways that have been shaping cosmic structure since the universe was young. And on that note, we conclude our journey through the mystery of the Great Attractor. We've discovered that what initially appeared as an invisible cosmic force pulling our galaxy toward an unknown destination is actually the gravitational heart of our own cosmic home, the supercluster that contains us. This enormous structure, spanning over 500 million light years and containing 100,000 galaxies, represents our address in the vast cosmic web. The Great Attractor teaches us that the universe is far more interconnected and organized than we might have imagined. We're not isolated wanderers in an empty void, but participants in a grand cosmic dance that has been choreographed by gravity over billions of years. Our Milky Way, along with thousands of neighboring galaxies, follows ancient gravitational currents toward the center of our cosmic neighborhood, a journey that will continue for billions of years to come. This cosmic phenomenon also highlights the remarkable detective work of astronomers who pieced together this story despite the challenge of studying something hidden behind our own galaxy's dust. Through ingenuity, persistence, and the use of multiple wavelengths of light, they revealed one of the most significant structures in our local universe and helped us understand our place within it. And so our cosmic voyage draws to a close. I hope these stories have carried you gently through the wonders of our universe, perhaps offering glimpses of distant worlds in your dreams. The cosmos never sleeps. It continues its ancient dance of stars and galaxies. Neutron stars pulse their rhythmic songs, and gravitational waves ripple silently through space, all while you rest peacefully here on our small blue planet. Thank you for joining me on this journey. If these cosmic tales helped guide you toward restful sleep, please consider sharing this video with fellow stargazers who might also find peace in the vastness above. Sweet dreams, and may your rest be as infinite as the universe itself.